So I think it's 9:30 sharp. So we will start because we have a big component of online people, mostly YouTube. Yesterday we had 300 people following on YouTube, which was a lot, a factor of almost 10 the amount of people that were in the auditorium. So I think that's quite nice. So it's my pleasure to have here João Paulo Sineker, he's Vice Director of CBPF, and will introduce the event. Thank you, João Paulo.
So, as Ulysses mentioned, my name is João Paulo Sineker. I'm the Deputy Director now at CBPF. My area of work is nanofabrication and superconducting devices and so on. So I'm a little bit far away from your area. But nevertheless, on behalf of the CBPF, I'm very honored to open this Open Universe event here and to host this event, which reflects the deep commitment of open science, international collaboration, and democratization of knowledge. We express our gratitude to the coordinators of this event, Professor Ulysses and Professor Paulo Giomini, who is outside, and also the support of the Ministry of Science and Technology, whose partnership strengthens our ability to contribute to the global space and science community. The Open Universe stands for a vital step towards making astronomical and space science data truly accessible for education, research, and citizen science. And I could not, I didn't help myself to make a quote here. I think the work you are doing, it's a very special work in contributing for this democratization of science and the space. The space should be really a thing for the whole humankind and the whole civilization. And I will quote the one thing that it's deep in my, how do you say, my younger life. So the space is the final frontier. And the Open Universe, it's a very good initiative to explore new worlds and to find out new forms of civilization, new life, and to boldly go where no one has gone before. So welcome to the Open Universe event. Thank you.
Thanks, João Paulo, and thanks for the quote. I think this resonates a lot with many citizen scientists. So now it's my pleasure, in the continuation of this introduction, to give the floor to Adriana Cursino-Tomé. Adriana is the General Coordinator for Multilateral Cooperation of the Ministry of Science and Technology of Brazil. And the Ministry of Science is the main supporter and funder of the Open Universe initiative that is then developed at CBPF, which is an institute member of part of the Ministry of Science. So Adriana, thank you very much for being here with us, and the floor is yours.
Ulysses, just before Adriana starts, I just want to say that I'm very proud, but I have to leave, unfortunately. I have many other activities as a deputy director, as you may know. So if you would like, any one of you would like to make a tour to CBPF to know other things we do, please contact Ulysses and we can try to arrange to the end of the week a visit or something like that. Thank you.
Thank you. Adriana, please.
All right. Well, ladies and gentlemen, good morning, good afternoon, good evening, depending on which part of the world you are. I think we have an international audience as well for this event. On behalf of the head of the International Affairs Office of the Ministry of Science, Technology and Innovation of Brazil, Mr. Carlos Matsumoto, I want to congratulate the CBPF, especially in the person of Mr. Ulysses Barres, for the organization of this outstanding event, which I consider a milestone for the Open University Capacity Building Initiative. I particularly want to express my personal satisfaction in participating in this opening session. I have been following Mr. Barre's efforts to launch this initiative for many years, and it's indeed a wonderful feeling to see what it was an idea now coming into reality. I'm confident that this event is the onset for a fruitful international cooperation in astronomy and space sciences for sustainable development. In a context of global challenges related to reducing socioeconomic inequalities, the fundamental role of science, technology, and innovation in building a prosperous future for all people becomes evident. The Open Universe Capacity Building Pilot event is totally aligned with the view of the Ministry that research and technical development must be conducted with an inclusive approach to ensure that technological advances benefit everyone. Global challenges, which by their very nature transcend borders, can use international cooperation as a tool to mitigate inequalities and inspire actions that foster equity, diversity, and inclusion. In this sense, investment in technology and innovation, the popularization of science, scientific dissemination, and the development of social technologies are essential to achieve this goal. In supporting this initiative, the Ministry is honoring the Memorandum of Understanding for Mutual Cooperation on Matters Relevant to the Exploration and Peaceful Uses of Outer Space, signed with UNOSA in 2020, and reaffirming the importance space has a strategic asset for achieving the 2030 Agenda. The Open Universe initiative, through expanding the availability and access to open source space science data and promoting capacity building, is a pivotal example of how international cooperation can be used to leverage open science and access of space data to all people using science, space, and innovation diplomacy to achieve the Sustainable Development Goals. Number 4, quality education. Number 9, innovation through scientific research. And number 17, partnerships. In conclusion, I'm certain that the event will contribute for the promotion of research in the fields of astronomy and space sciences, enhancing the accessibility of space science data and closing the gap between researchers and society, thus enabling that the benefits of the space exploration reach a greater number of people globally. I hope this is the first of many other events within the umbrella of the Open Universe initiative to come. I wish you all a fruit-bearing days ahead of you. Thanks for your attention, and a special thanks for my colleague Ulisses Baez.
Thank you so much, Adriana, for your kind words and the introduction to the event. Now it's my great pleasure to show you a video that Ms. Arti Rolamaini, the director of the United Nations Office for Outer Space Affairs, recorded for this event. And this reflects the support that the Office for Outer Space Affairs of the United Nations strongly gives to this initiative. And in fact, the office has accompanied the development initiative since the beginning, as I will explain in my initial presentation next. So it's a pleasure to have Arti Rolamani giving this introductory speech to us on behalf of the UNOSA.
Distinguished guests, esteemed colleagues and friends, good morning. I'm delighted to be opening this first webinar as part of the Open Universe Initiative. UN COPUS, the United Nations Committee on the Peaceful Uses of Outer Space, is the main UN body responsible for space-related matters. Today, the committee represents 104 countries and more than 50 observer organizations. In 2021, after reflecting on more than 50 years of achievements in space, member states adopted the Space 2030 Agenda, Space as a Driver of Sustainable Development, in the General Assembly. The Space 2030 Agenda aims to ensure that all countries can benefit socioeconomically from space solutions to support the achievement of the Sustainable Development Goals. The agenda defines the activities and tools that can be used to promote the use of space-based solutions. And one of the tools explicitly listed in the document is the Open Universe Initiative, designed to enhance access to astronomical and space science data. This initiative was conceived to create new opportunities for capacity building and education by improving the use of open databases and online resources. It's part of a variety of capacity building activities that UNUSA, in cooperation with partners, will implement for the 21st century to progress on the Sustainable Development Goals. Our cooperation with the Brazilian Ministry of Science, Technology and Innovation, MCTI, dates back to 2020, and we're now really pleased to see that the long preparation of work is bearing fruit. Although I'm unable to join you in person, as director of UNUSA, I'm delighted to see the large interest that has been shown for this initiative. Thanks to the Brazilian Center for Physics Research, CBPF, the Open Universe Initiative is moving ahead with this first event, and we're looking forward to more such events in the future. You may know that just a few weeks ago, we concluded the Scientific and Technical Subcommittee of COPUS, known as STSC. The astronomy community are active participants and ready to discuss emerging challenges. For several years now, the exponential number of satellites being launched has created issues for astronomers, either because some of these satellites emit radio signals or because they reflect sunlight into astronomical telescopes or cross their field of view. This has and continues to have the direct effect of limiting astronomical observations. Many years of coordinated action among astronomers, however, has resulted in having the issue discussed at the highest international level, with a new item on dark and quiet skies added to the subcommittee's agenda until 2029. This is an important matter where UNUSA collaborates with all stakeholders to find a balanced approach between the advantages brought by satellite services on the one hand and the need to preserve the view of stars for science and society on the other. In April this year, 2025, we will celebrate the 35th anniversary of the launch of the Hubble Space Telescope that revolutionized our understanding of the universe. Astronomy and space science are important topics of international scientific collaboration that inspire so many young people to seek a career in the space sector. Together, we need to leverage the potential of space to continue to inspire the youth and increase the involvement of young people in the space sector. In this perspective, I see a great potential in Open Universe as a platform for capacity building and international collaboration, and I'm looking forward to the productive collaborations that will result from today's event. Thank you so much for having me with you.
Well, it's really indeed a pleasure to have the contribution of the director of UNOSA, and of course the support of UNOSA is fundamental to boost and to give strength to the activities of the initiative. And also I'd like to note and thank the presence of Nathalie Ricard, who works at UNOSA, as an officer from UNOSA, and is present here following the event as well, and has tremendously helped the development of the initiative and also the putting together of this program, particularly on the side of the dark and quiet skies that the director just mentioned. And yesterday we heard a little bit from Tanya, and we will hear a little bit more tomorrow. So I guess with this, we can move to the more technical session or technical part of the event, having finished the introductions. And I will start introducing what's the Open Universe Initiative. So some of you were already here yesterday for the event, which was more focused to teachers and students. But I'll go through some of the things that we already presented yesterday and perhaps a little bit more in depth, given that you also have followed some of the activities that we do through the program that we had yesterday. So as mentioned, the Open Universe Initiative is a capacity building initiative, which means that its scope is to use the tools that we develop for research to impact in the formation of human resources, in the education, and in the transference of skills that are important in these kinds of activities that we do in space science and astronomy, but are also meaningful and impactful for society. The initiative originated as an idea long ago, around 2016, 2017, through, as we already mentioned yesterday, the initiative of Paolo Giomi at the Italian Space Agency at the time, who proposed the concept of the Open Universe Initiative as an answer to a call in preparation for this very large conference on space called Unispace Plus 50 that took place in 2018 and was built already on the perspective of the United Nations Sustainable Development Goals. And the motivation of the initiative was to expand the availability and the access to open source space science data. So data that is anyway already open, but not easily accessible to the public, to deliver capacity building and the development of skills that are important for the 21st century society, which is a society based on technology, on data, on information, and on science somehow. The motivation behind it that justified the launch of this idea was basically had two pillars. The first one is the fact that more and more data is being produced in large quantities in space science. We are flooded with data from observatories, space missions, and most of this data, because it is produced with public money from the governments and the funding agencies of science, it is anyway available to the public. It's available to all scientists worldwide. So there is a treasure trove of information, scientific information, that can be used to do capacity building. But of course, the difficulty is that not all of this data is easily accessible. So it remains closed in effect to a small number of people. The second thing is that more and more we have new technologies. And when we started discussing the Open Universe Initiative in 2016, 2017, nothing like the kind of power of artificial intelligence that we have today was available. So more and more, and in an extremely fast pace, data technology, information technology is developing and making things more accessible to all kinds of people with all kinds of background anywhere in the world. So there is a potential to harness all this information, scientific information, to do capacity building, to develop human resources in fields that are useful in terms of skills for the industry and for the society of the 21st century, and in truthful scientific information, which is very important for our society nowadays. So just for you to have an idea of the evolution of the amount of data in astronomy. So this shows the amount of data that is produced in petabytes over several years. In gray, you can see the amount of data produced by the largest experiments in science in the world, which is the large particle accelerators, for example, at CERN. And you see that they produce huge amounts of data in the field of particle physics. But astronomy is quickly catching up. And in fact, with the new instruments, for example, like the Cherenkov Telescope Array, or which is a gamma ray observatory with which I work, or the Square Kilometer Array, SKA, the amount of data being produced by astronomy is really catching up with the field in science that already produces more data than anyone else, which is particle physics. So there is a huge amount of data available, which is even difficult for the astronomers to analyze, simply because there is so much data that there is not enough people and enough availability of computer power to process these things and extract meaningful information from them. So there is also a need to justify the production of all this data, to make it more effective, to include more people in participating of the science endeavor, so that you can justify the investments and make all this more productive for society in general. This plot was shown by Paolo Giomi yesterday in his presentation, and it shows a little bit where we aim to go with the open universe. So if you look 25 years ago, or now it would be 30 to 35 years ago, because this plot is from 2016, 2015, where people like Paulo started doing his work, pioneering the work in astronomical data, the amount of data that was produced was very limited. There were fewer observatories producing less amount of information, fewer space missions. They were just starting many of the fields of astronomy. And in fact, the amount of people that were able to deal with this data, do science with this data, in any case, understand and extract information was very limited. Were only the few tens of specialists that were, in most part, participating in the construction of the instruments that then was making the observation. So things were complex. Data science was still in its infancy, and it was very difficult to access this information. It was very, very limited to only a few people. As time passes, information technology developed, and more people started to be able to participate in the data analysis of observatories and missions. Initiatives like the Virtual Observatory, which you heard of yesterday, that puts lots of efforts over decades to make astronomical data in a format that is interoperable. So following same protocols that can be exchanged between scientists anywhere in the world, and that can be combined from different instruments to produce the plots, for example, that you have seen in the Firmamento platform yesterday. This all allowed that scientists, for example, that are not part of a specific sector of astronomy could use data from other sectors from where perhaps they are not so much specialists. So this increased the reach and accessibility of data. And this continued to be so as information technology evolved, and this is the situation of today. But still, there is a huge potential. We are talking about 10 to the 4 scientists that, so a factor of 10,000 of scientists, of people in the population of the world that are able to use this information directly without intermediaries. Of course, we know something about this information when we see a picture of the Hubble Space Telescope in the newspapers, but we are not dealing with the information firsthand. We are hearing about it. So of the whole population of the world, few tens of thousands of people can deal with this data. But there is a huge community, as we are learning, of people that are interested in science, that would like to participate in it, that through science could have their lives transformed, as we saw the testimony from the students yesterday, from the students from Padova. And this number is a factor of 1,000 larger than the number of people that today can access the data directly. What the initiative wants to do is to help to bring this data to these people. And there is a lot of work to do towards that, even with the virtual observatory, even with platforms that are already in place. There is still a lot of work, but the benefits can be great, as we have seen the testimony yesterday. Also, for the sake of science itself, it's very interesting because by involving more people in this endeavor, we increase the amount of knowledge we produce from the data. The example from Padova we heard yesterday, the students contributed in the discovery of new sources, production of new scientific information, new catalogs that were not there before. Of course, they were available. The scientists could have done it, but there is only a limited number of people working on the field. So there is even discoveries to be done by citizen scientists. And that's why this becomes so interesting. And of course, also in terms of justifying the work we do for governments, for the funding agencies, if you produce more knowledge out of the same amount of data that you are generating anyway, you diminish what we could call the specific cost of knowledge, and you also democratize it. So it's a win-win situation, but there is a non-trivial bridge to be crossed to get there. It's very hard. Somehow, it's much harder to do this job than to do the job of the scientist itself, because we are trained to do our job, but we are not trained to do citizen science and to bridge to you. And this is something that we want to learn with you and following this path together. So Open Universe is not done alone by us, by myself, by Paulo, by the other colleagues that are present here. We already heard that it was created under the auspices of UNOSA and has a lot of support from the United Nations. That is crucial for us. It's supported by the Ministry of Science of Brazil. This house, CBPF, puts a lot of effort from the technical side for the infrastructure that we have. But there are also partners, and we are looking for more and more partners around the world that are trying to do exactly the same thing that we are trying to do, creating platforms, developing tools, making events to reach the citizen scientists. But by working together, maybe we can boost our capabilities. And the Open Universe wants to be a help to reach the public and to do this communication. So here are a few of the partners that we are working with. Some of them, for example, Firmamento was born out of the work of Open Universe this last, or of the preparation of Open Universe these last 10 years. If you go to our webpage, you are going to see several scientific papers that were published associated with the development of the software that you're going to use over the week. And some of them are in this platform called Firmamento that was developed by Paulo and funded by the New York University in Abu Dhabi. There is also the Markarian Data Center, which was also born in the middle of this concept. And we have here Narek Sahakian from Armenia, who is going to talk to us about this, which is a very interesting tool full of artificial intelligence into it. So really at the edge of even what the scientists are doing today, but which wants to make data more accessible to the public in general, and also for the scientists. The scientists benefit tremendously of this as well, because you facilitate everybody to access data. So the objectives behind the initiative, and this, as you can see here from the bottom of the page, they were the result of discussions that happened in the year 2017 under the auspices of the United Nations in a series of workshops that we had both at the Italian Space Agency and at UNOSA in Vienna, with the scientific community, with the presence of colleagues from the Virtual Observatory, with the presence of the International Astronomical Union. So a huge effort to discuss what would be the purposes of such an effort. Or is it worth it? Should we go in that direction? And in fact, we confirmed our intuition that there was good things to do in this. And we also identified, with the help of these colleagues from the scientific community, what should be 3 main pillars for the activities of the initiative. So the first one, which is the most important of all, because it sits at the base of the other 2, is to increase transparency. As I said, a lot of data is open. Many satellites from NASA, and today you are going to hear from one of them, which is the Swift XRT instrument on board a satellite by one of the experts of this instrument, which is a mission funded by NASA. And the data is available almost instantaneously. It's downloaded on the server and you can access it almost instantaneously. But if you are not an expert, it's impossible to extract anything from it. And that's fine because it's a scientific instrument. But the question is, how can we make this data more accessible so that more people can use? Of course, you cannot expect a citizen scientist to deal with this data in a very sophisticated, deep way. You need years, decades of training. And some of the users of the data, only the people who build the instrument will ever be able to do, because you really need to know how every photon is detected and what is behind the instrument in detail. But there is a lot more high level, even for the production of real science, that can be done. And by doing that, you include society in the scientific endeavor. You explain how the scientific method works. You teach lots of things that are important for society today. So to increase transparency is fundamental for us. And you have seen, for example, the example of VO, the Virtual Observatory, which built all the protocols and all the tools that are the basis for all these platforms that we are showing to you. And you already saw that it's not trivial to get intimate with it and do things easily. Even a set of tools like this, which are very accessible for university students, for example, for the larger public, are complicated. So there are more steps to be taken. To resurface data is another important thing. There is a lot of data that is produced and never sees the light of the day. Of course, the main missions, this doesn't happen. The main satellites of NASA, of the European Space Agency, all data has to have a destiny. There is a lot of control. There is a lot of money invested. There is data centers. But there are medium-sized observatories, small-sized observatories that don't have even the capability to publish their results properly in a way that is accessible or analyze the results. Maybe this can be a way to help these small observatories also, so that their existence remains justified. And these are especially important for small centers or places that are far from the big research areas, in continents like Latin America, South Asia, Africa, etc. The other important thing, which is perhaps the consequence, is to broaden the user base. By doing all this, we include more people in the scientific endeavor, which is what we are really looking for. So just some additional information on some of the things that I said. During these workshops that we made in preparation for the initiative, we had one colleague with us, which was actually an economist that worked then for the Italian Space Agency, but has an economist background, Massimo De Angelis, who made a study about transparency and things like this, and transparency of data. And this is very clear to understand that to have availability, which is what we have very well, doesn't mean to have transparent or accessibility. No, you can have data or a high availability of data, but you can have transparency that is called mute or speechless. So the open data is only useful for experts. It could be closed because no one else is able to use it anyway. There is also what we can call an apparent level of transparency. So the data is very highly accessible, but its usability level is very low. You can do very few things with it, with the tools that you have available. You can have partial transparency, which is a bit better, but what we are looking for in things like Open Universe is what Massimo called the communicative transparency. So that the data that is available talks. You are able to extract, you are able to hear what it has to say without having to know too many technical things. Of course, if you're an expert, the data will talk much more emphatically, but it still can tell you something, even if you are a citizen scientist. And that's what we are looking for. The cost of that, the cost of going from the experts in complicated computer interfaces of the 80s to the whole public, so from going from raw data to knowledge, is the cost of computer processing. So the data has to be treated, and you have to develop a number of sophisticated tools that hide all the complexity of dealing with the information technology aspect of the data, so that when it arrives to you, you can do something with it, even not being an expert. And it's important that this process of producing this information be done by scientists in an authoritative manner. Otherwise, also, you don't have access to trustworthy information, which is very bad. So there is a long way in this process, and this is what is behind the work of the Open Universe Initiative and other initiatives of the kind. So if you go to our webpage, you see there are tens of scientific papers produced, because to do this step is actually to do high-level science, which is useful for anyone. So by doing this work, we are also producing science that is of our interest. But the message, I guess, is that we can do our work with a look towards a bigger horizon and a bigger public than simply the academics. So since the initiative was born in the context of the Sustainable Development Goals, or the preparation for the activities towards the Sustainable Development Goals of the United Nations, we paid attention to try to use the initiative to answer or help in achieving some of them. And the ones that really dialogue with the initiative more evidently are very clear. Quality education, by having access to web-based content and tailored online capacity building activities, we can help teaching at schools. It's one of and we saw an example of that yesterday. Through the portal, not only access to data, but also through virtual courses, training sessions like we are doing here, the videos of events that are recorded. All this provides access to knowledge that's useful. Reduced inequality is another important thing, because it's very different, the experience from doing outreach and citizen science in certain parts of the world, or depending on the sector of society that you choose, than others. So really there has to be an effort to reach the people that need the most, are least prepared, have least background, so that we can make this access democratized to everyone. And this is an important thing that we are looking for in the initiative. So really to leave no one behind, and trying to make a bridge that then anyone can cross. And there is a little typo here, but the other one is the Sustainable Development Goal 17, which is really to strengthen the means to implement the activities that are being developed. There is to build partnerships, and we really value to build partnerships and create relations that with groups and activities that want to go the same way as us, so that we can help each other. So really building together. There were some steps that were taken for the development of the initiative, and I put here this list just for completion and for the records of the meeting. Also, because if you click then on the slides that will be available, you can see all the formal documents that were produced in the context of the United Nations for the initiative. So we had an expert meeting, and you can find the documentation out of it. There was a workshop convened by the United Nations to discuss the initiative in 2017. Here you can see the report with all the discussions that happened, with all the inputs from the various groups, various countries that participated and shaped what we have built now. There was a report that was produced by UNOSA that is also available here. And in the end, there is the Space 2030 agenda that was published in its final format. And that was mentioned by the UNOSA director a little bit before, includes the Open Universe explicitly as one of the initiatives of the office for the Agenda 2030. So this is a big responsibility, but also a big help, because this really trusts us to go ahead more strongly. Adriana mentioned the MOU that on the end of this long path of preparation was signed between Brazil and UNUSA, where the Open Universe Initiative is included. And this is what gives the support for us to be able to do an event like this now, really starting this series of activities that we expect to take ahead with the initiative. So all the instruments are available. This is a pilot event because, as I mentioned, to do citizen science is not something that we learn at our usual training. So we need to understand from you what works. So it's the start of a dialogue. So I don't think the initiative finishes here or concludes here. It starts here. All that came before was preparation, and the pandemic ate some years from our efforts, because for obvious reasons it was difficult. So in the end, the answer we want to, the question we would like to ask, that is the boldest perhaps, can we contribute to build a knowledge-based society? This will be, in a way or another, the society of the future. Information dominates the way our society works, but it can be information that's full of fake news, not trustworthy, that can be filtered in ways that the citizen cannot understand simply because it doesn't have a grasp of data and factual information. Or it can be a society where the citizen is empowered to question the data, the information by itself, and more strongly, so that it can counter lies and fake information that could drive society in a bad direction. So a knowledge-based society, I believe, is a very difficult dream, but we should, no matter how difficult, try to do activities to reach it. And this is our way to try to contribute to this. And you have seen yesterday the fantastic example, I think it's really fantastic, of the colleagues from Padova and we heard more than their results, the catalogs they published and the discoveries they made, their testimony. And it was very clear that not only the experience of being able to participate in the adventure of science, which is one of the greatest, most pleasureful activities of humanity and fulfilling that exist. So they were able to participate in it, but how this can build lives. So they were really speaking about finding a career, understanding a vocation in science, but more than that, of feeling fulfilled, of knowing a new gaze towards the world, and becoming happier for being able to do these kinds of things. So this is really important. So we can build lives through this. I must say that there was a few events in the past 2 or 3 years that have prepared us to be here, basically centered around, or mostly centered around, the Firmamento platform. So there were trainings that helped us to understand how then to be at the position that we are in dealing with the public in the New York University of Abu Dhabi in the 2 previous years. And this has helped us to prepare for where we are now. So in these days, so we had already yesterday what we call the education workshop, where we had many presentations in Portuguese, really trying to bridge to students and teachers at schools. And now we have a sequence of 2 days of workshop, more to the citizen scientists. They will be fully in English, and then 2 days of Sciathon, where we expect to have some hands-on activities with you on the tools of the initiative and things that you'll be seeing these days in the presentations. So this is the program. I don't have to go in detail through it, but there is going to be some contributed talks, and I would like to highlight here there are students that are going to present their work, professors, but also to highlight the presence of the Brazilian Space Agency, who is also going to give a presentation on the kinds of activities they do for capacity building and outreach. And of course, we are interested in doing things together and potentialize what other people also are doing in this direction. So it's very positive to have them. I'm very happy also to have them here. The Sciathon will be based on producing data out of this instrument, the satellite instrument Swift XRT, and you are going to listen to a lecture now by Paolo Giomi about X-ray astronomy, and then Giampiero Tagliaferri from Italy is going to give a lecture on Swift. He's one of the world experts in this instrument, worked since the dawn of the instrument, the creation of the instrument, and is going to give a very detailed presentation of what this instrument is. So you are going to see where you are going, what kind of data, where is the data you're going to be dealing with coming from, how complex it is. And well, let's see if we have been successful in making it at least a little bit accessible. You might conclude in the end that we were not, but it's worth the try. And the idea is to produce a kind of legacy work of citizen science. So strangely enough, instruments like this, for example, if you want to go to the internet and say, oh, this instrument is taking data for 20 years, can I find the sky map of all the observations that this instrument made? No, you cannot. Why? Because it doesn't exist. So the proposal of this Sciathon activity is to build a fully based, full sky map of the whole history of this space mission, so that you can browse and see, built only by citizen scientists. It's a bit mediatic in the sense that, no, we choose something that has images and it's like to see, but it's really to make a point that there are things that you can contribute to that are attractive for the public in general, so really can keep your interest, but also useful for the scientists, because this data will then be available for download from Open Universe and will be data that is ready for scientists to use in their work. So maybe they can thank you after they publish their papers. And the idea is that everything that we do in this way stays as an open resource for everybody, and is really meaningful also from the scientific point of view. So we believe that citizen science has to be real science as well. It's not just a little game, but it has to be real science as well, and it can be. This is much more interesting. So yesterday we had the first session of the education workshop. Along the day we had 300 people following on YouTube, which is really impressive. So this, I cannot say it's a success because it depends on how it was received, but at least we are confirmed in our intuition that there is a lot of people interested in this. So it is indeed worth the effort. So we had 800 people registered. So maybe over the day, the sum of this count will go to that number. And of course, citizen scientists have jobs, they go to school, they are not available all day, every day for a conference. It's difficult. So we also have to understand how to make this bridge. And there are ways, YouTube, Zoom, these help a little bit. So, but the fact is there is interest, and we should continue pursuing this direction more and more, and question ourselves all the time, how can we better reach? But anyway, all this will be available. We created a YouTube channel for the initiative. So everything we do will be posted here. And our intention is to organize the videos then in separate lectures so that you can go back and you don't have to browse through 8 hours of programming each day to find what you're interested in. And that's it. So as I said yesterday, the message is, let us build it together. This is not the end. So you are not dealing with a final product. This is the beginning. So, and we need you. Thank you. Good. Any questions? Yes.
So thank you for the talk. It was very good. For new observatories that are idealized, what's the expectation for open data? Because I believe that the scientists that idealized the observatories want to be the first to publish the results. So like the open data will be like the expectation is to be available like after 5 years or after the observations, or like in real time. Is that a problem or something like that?
It really depends. So he's asking about the availability of data in observatories in general. And the policy really depends on the country, on the funding agency, on the field of astrophysics in particular, on the kind of instrument, on the availability of resources, because to publish has a cost also. So it varies. But what has been a trend is that more and more there is a push from society, so from governments, because these experiments, these instruments are built with public money, to make the data available to anyone. And there is a push, and we hope it's not reversed, to make this data available to anyone in the world for increased international cooperation. There is a big bit of a question mark nowadays for this, but we hope it's, at least in the scientific community, we don't go back too many steps. And so the expectation is that more and more data will be available quicker and in a more graspable and usable manner. No, of course, if you spend hundreds of millions of dollars to build an instrument, and this instrument is going to do important discoveries that will change the face of science, that can lead to things like Nobel Prizes and things like this, of course, you have to retribute in some way the country that invested the money, the people that have invested in building it, etc., etc. So usually this data has what we call proprietary time. And also because the data, when you first see it, it's not obvious many times how it's working. So we all have what we call commissioning time in experiments. So you produce the experiment and then you start to take data, and it takes a year, perhaps sometimes, to understand exactly what that data is before you can publish a paper and say, I trust this information. So this is normal, but as I've shown, there is much more data than any proprietary time can analyze. So I think if we make this little effort of making data centers more and more easily accessible, everybody will gain. No? And there was a study, Paulo John will probably remember better than me, during one of these Open University preparatory workshops almost 10 years ago, where there was an economist actually talking about the economic relation between making the data open or not in terms of scientific returns, in terms of dollars, which is really in the end the metric that you have to use. And the investments that you have to do for a data center is not banal, but it's a small fraction of the effort of producing the instrument. And the potential reach that you have is orders of magnitude higher than that. So, for example, instruments like the Hubble Space Telescope, they have more papers published out of archival data than papers published out of the data analyzed by what we call the PI, so the scientist that was leading the project. Without the archive, the productivity would be less than 50%, what it actually is. So there is a win-win situation there, but it's and information technology developments are on our side. And I expect data to be more easily available. Your field is cosmic ray physics, I know, and that's a tricky field. So you are looking from the most difficult science.
I have two comments, and so look around if there are other questions, because maybe I don't want to take too much time. The first one is, I was recently in Bologna to a meeting organized by INEF about, if you want, data preservation, okay? And so we understood that we have a problem in the community because if you don't prepare, you make an experiment. You're happy, you develop many things, then you have your data, then you analyze your data. And at the end, then you say, okay, then I want to share my data with the people from outside as a legacy. But if you do this at the end, it's very complex to do it. A data preservation and dissemination plan should be done from the beginning. Okay, this is something new and it's part of this, etc. So, but I see that new facilities, they start to have it from the beginning. What was discussed there, and actually I think it's a good idea, and I don't remember if, but anyhow, it could be part of Open University initiative, is to have like a certification that the data management plan is good. You know, like ISO 40001, no? Which tell that a process is good. This you cannot make, it's not a commercial thing, no, but you can support, because there are many things. I realize in Bologna that there are many things that if you don't know, you don't know, no, you don't know the unknown unknowns on how to do this kind of thing. So it would be great if it's not that complex, but you just define some things, and then an instrument can say, okay, I follow the Open Universe data management plan suggestions, so that at the end I know that I can share my data in a good way. So that's my suggestion as possible new field of Open Universe initiative.
Well, I think Paulo has his camera closed, but he would be, I think, jumping on his chair, listening to you, because this is something that he's pushing for since the beginning. It's actually something we had some partners from a university in Naples that were looking into this, and there is Paulo now jumping for everybody to see. And so we started discussing this for some time. It didn't go ahead, but I think it's an important thing. It's part of the ideas that Paulo has as a goal for the initiative. Of course, the challenge is to have a good team to do this. Of course, you have to start from somewhere, and then the thing grows and it's criticized and it evolves. And you have to have an authoritative body behind, because if you are going, yes, and there is the United Nations logo there, maybe we can discuss. But because you'll be telling, the pretension of this is to be telling NASA, ESA, these guys, that if to develop some standards that they would perhaps have to follow. So there is work to do. But I think, Michele, you are right. But let's listen from Paulo.
Yes, well, it's a tough thing to do. It's obviously a very nice and obvious thing to do that, as we stated from the very beginning, when you plan a budget to run a satellite or a mission, very costly mission, you have to make sure that the 1% money that is needed to make sure that the data is available to everyone should be in the plan from the very beginning. And how to do that, there could be standards, and we could define standards, but then you have to convince NASA, ESA, ESO, NCSA, all the big agencies to follow your advice. As you well remember, Ulysses, we had a lot of discussion there, and it's going to be not easy. Maybe it's worth under the auspices of the United Nations, maybe. But if you remember, our friends in the VO, they said one of the criticisms they were saying was that the United Nations is not the right place for this thing to be done, which is not what we thought. So it's a political thing. I completely agree that it should be done. And the gain for that is that we would ensure that the people will get benefit of the data. So it would be a great achievement, but not an easy one. Maybe this workshop could be a restart for the discussions that will inevitably be long, but our view is a long-term view, and maybe we could think of moving, trying to push in that direction more than we've done before.
Yes, I mean, and the VO is participating in this event. We have a lecture yesterday. We're going to have one today by Ada Nebo, who was one of the leading people at the center of Strasbourg, which is one of the key centers for the virtual observatory in the world, in France. And within the scientific community, they have done technical steps that essentially, without giving a certificate, kind of put some standards to be followed. The community has adopted it over the years. But what we are discussing is much more. And it's really data management standards in all aspects, not just protocols. We also have seen from Tanya, we are going to hear tomorrow from the people working in SKA, one of those instruments that I said that is producing huge amounts of data about dark and quiet skies, which is an initiative that was born in the astronomical community and was taken up by the United Nations together with the International Astronomical Union to really give, and is giving amazing results, and has gathered the political support necessary for dealing with a matter as difficult as protecting the skies and the orbit, which is very political and very economical. So, I mean, we are among the people that could help us do this. So maybe it's a process that we would like to start discussing. Of course, the International Astronomical Union is a very important body for that as well. And we have many friends there, many colleagues. Maybe, Michele, your question is really good, or your comment is really good, because it reminds us that we should not forget of these aspects.
Okay, and the other point, I think we have 4 minutes, no, before the coffee break. This we discussed already in Abu Dhabi. I think it would be great because Open Universe, still not clear to me who is exactly. There is a, well, I know now there is a web page, but there is a mailing list. I don't think the information flow is very structured. So I think you should work on that. But I think it would be great to have to define a figure of Open Universe ambassador that is a knowledgeable person about the activities and the tools, okay, a little bit, because, okay, I cannot come to Brazil that often, you cannot come to Europe, etc. No? So if in each country or several countries we have a contact, okay, an ambassador in this sense, which is knowledgeable on the activity, I think this will boost the activity, and it's an easy thing to maintain. No, it's a mailing list and people with knowledge that can organize more little workshop.
Okay. One thing, hello, Jamie, by the way. One thing I think that's particularly exciting is the possibility of STEM professionals getting involved. I think they're certainly going to help with the bridge. From my perspective, at least, we've just started discussing and looking at what STEM possibilities might help achieve. And I think it's really exciting that Italy and Brazil have come together to really take this forward. It's just fantastic that the people from here, the people from Italy can feel good about themselves. You know, it's our project. I think that's delightful. Rather than following other people, we can give them the opportunity to celebrate themselves. And with just a few more professional people enlightening the path, if you like, opening it up, not just the scientists, but the professionals as well. I think that the people have the opportunity to really believe in themselves and what we are actually trying to change and do together. It's brilliant.
Thank you very much. And listening, this encouragement from a citizen scientist is means that, well, at least we are speaking in an understandable way and we make sense. Yeah, so tomorrow you are going to listen. The first lecture will be by Simonetta Di Pippo, who was the former director of the United Nations Office for Outer Space Affairs. And I think she's going to touch on some of these things that you mentioned. And of course, Michele, your idea of the ambassadors, I mean, there is a lot to be done. We are building. It's very good. Maybe you can be the Minister of Foreign Affairs so that you can take care of the ambassadors. Yes, so I don't know if there is any questions or comments from Zoom. I don't, if there are any questions from YouTube, I can read them aloud, but I see none. So if there are no comments or questions from Zoom, I would say it's time for coffee break. Ah, yes, Leandro.
Hello, just another question, but have you because there are like hundreds of mini satellites that goes into space every year, and most of these data are not, I mean, they are usable only for the people that actually launches them. But I think in this matter, we should also take all those data so that people can use it, for instance, for transient events or some where timing is important. I think having more and place them all together could be very important, not only for citizen scientists, but also for scientists.
That's true. And again, Paulo is jumping on his chair because this is one of the, we are very few, but we've been there. So this is another thing that we did discuss a lot. And in fact, with Carlos Brandt, who is going to give part of the Sciaton training in the last 2 days, is a Brazilian that studied here and then became a student of Paulo in Italy. We discussed the building a software tool that does exactly that. So one of the difficult things of publishing this data is because maybe you know how to launch the microsatellites, you can produce the instrument, but maybe you don't know to a great extent VO protocols and software so that you can publish it online in an accessible way to everybody. So we were talking about for a long time developing a container, a Docker tool, which you simply download from the internet, you install in your computer, you give the data in a very simple, basic format. It has to be flexible as well, otherwise it doesn't work. But it does all the job of publishing this data for you. So it's like a virtual data center that with a couple of clicks, you transform your computer in a data server. This can be done. The technology is there. It's not impossible, but you need someone to do it. So then Carlos went to do other things. He has a job. We have other things to do. And this is one of the things that we thought of, but never done. It would make a huge impact. but we need someone to do, we need someone to maintain, we need some resources, and this is not trivial. So there are many ideas, and it's good that 2 of them already come out. So it means that they were not crazy, they are not outdated, and they need to be done. But we need partners. So maybe it can be a citizen scientist that is a computer geek, could do this job, or someone that is a professional would be interested in doing this, cooperate with us. But yes, there is a lot to do that can really change the landscape. And it's not so difficult, but we just need the ideas and then to push them forward. Right, Paulo? I don't know if you want to comment on this. You are muted still.
To click on the right part of the screen to unmute. Sorry, I was clicking in some wrong area of the screen. Yeah, obviously, all of these ideas have been discussed before. We should do that. As always, you need resources. We never really got enough resources to do all the ideas that we've put forward. Some people, I remember, criticized us because they were saying what we are proposing are good, but it's very expensive. Now, this is really not the case because building something like you just described, some facility that converts the complication of a complex satellite, even if it is a microsatellite, it's very complex anyway, into something that is usable by everyone. You need time and expertise and being able to do that. And if you have something that makes your life easier, then it makes it feasible for many data providers or people who build that kind of satellites. But the cost of producing this was something that it can be used by many people. It's an extremely tiny fraction of what is the cost of producing the data. One big satellite is 1 billion euros. One small satellite would be maybe 100,000 or so. But having a few thousand euros to build this is really, or maybe even a few 10,000 euros to build something like that. It's nothing compared to the benefit that people will get. We just have to convince somebody to give it, to provide the money and infrastructure to start doing that. At the moment, we're in a phase where we have a lot of ideas. Converting ideas into reality, it takes organization, money, and time, and resources. That's what we need.
Exactly. And in fact, for example, we saw the Astrocolibri 2 yesterday. Now we are going to see more details tomorrow. They are an excellent potential partner for that because they deal with transient data, and they allow you to publish in their platform your data to be instantly shared with anyone. So maybe there is a partnership there for this. No, we have to talk.
Hi, Ulises, thank you very much for this interesting discussion. I don't want to extend this interesting discussion, of course, further, but just to mention that there are other initiatives. I mean, Open University is quite nice to see, but it's an old question, isn't it? I mean, since the beginning of science, we are trying to make it publicly and be useful for society because what's the purpose if it's not like this, right? So engage more people and to build or to develop public scientists, as you call it, citizen scientists, right? So what I note from my side, I'm part of the CDIO community, which is a very good community that works on this topic of documentation or keeping quality as Michele posed it, right? So this is a European community started there in some universities. And now there are universities here in Brazil that has adopted, and in Latin America also is slowly growing. Yeah, but they build on top of these 4 pillars that is conceive, design, implement, and operate. That's why CDIO. So they are good on keeping standards. And they have lots of the documentation. They have these conferences that are produced yearly, and their mother is on how to build a good quality of education. So this is at a point something that you need to deal with, right? Because as it is starting as a new thing, you will for sure endeavor or deal with such a thing. So just in any case, I'm, let's say, a part of CDIO community already, participating in this initiative, of course. So it's a way to close this gap. So it could be interesting to see this like a match, right? So makes sense to build on top of previously built infrastructure and not to start from scratch, for instance, right?
Thank you. So I guess with this, it's time to go for coffee. So again, I would like to thank the support of CBPF, the ministry that is funding this event, and of course of the United Nations Office for Outer Space Affairs. Without these three, we wouldn't be here for sure. So thanks for believing in the initiative for almost 10 years and supporting us. the program by heart, to welcome Paulo Giomi, the father of the Open Universe Initiative, I should say, and the original proposer from at the time at the Italian Space Agency, and who is a famous X-ray astronomer pioneering in all this work with data and catalogs over decades. And today he's going to make us an introduction, a general introduction about X-ray astronomy, which is going to be the scientific topic of our hands-on activities towards the end of the week. So that's why we chose this topic. And then another colleague of ours, after Paolo, Giampiero Tagliaferri, who is also based in Milan at the National Institute of Astrophysics of Italy, like Paolo is now, will talk about the specific mission whose data we'll be dealing with, which is the Swift XRT. But Paolo, to start with you, with X-ray astronomy, thank you very much for your availability. And please, you can start.
Thank you, Ulysses, for a very nice introduction. Let me share my screen. Here we go. Okay, I assume you see my screen. Okay, today I will be talking about X-ray astronomy in general, as a general topic. As you see, I've chosen as the first slide an image that is an X-ray image, and maybe you don't realize it, but this is the Chandra Deep Field South. That's the deepest observation ever made in X-ray astronomy. So we start from the very end, at least from the most sensitive observation ever done. But let's go from the very beginning, very beginning, because in one slide, I try to summarize the whole history of astronomy. That's quite a challenging task. So let's start from the very beginning, when people were just looking up with their only technology, which is not too bad, but what we human beings have is their eyes. So at the beginning, of course, the astronomy was naked eye astronomy. Nevertheless, they've done a few things. They also had they had the human vision and very simple tools like the megalithic structures like Stonehenge. And this lasted for many centuries. It was not until the 17th century, in 1609, when Galileo Galilei managed to build a telescope using lenses. So it was refracting telescopes. That moved the sensitivity from what our eyes can do to what a tool can do much better, a telescope. Then Newton instead used a reflecting telescope like the ones that we're using now, but also refracting telescope we're still using. Then we need to wait another couple of centuries before a major evolution came along. There was the use of photography and the development of spectrographs. So we have photographic plates instead of just looking with our eyes into the telescope. We just put the photographic plates and then we wait for a long time and then we integrate and we get a much higher sensitivity than what we could do with our eyes. Before this, people had to look and then draw drawings by hand. Clearly, a photographic plate was a major improvement. We also had spectrographs. The light was not only useful to produce an image, but also it could be dispersed into energy and have a spectrum, which for physics is a much more valuable type of information. So this side of the slide is basically goes through many centuries, but always in the visible part of the electromagnetic spectrum. To move away from the very tiny part of the electromagnetic spectrum where our eyes are sensitive and where the sun mostly emits its radiation, we need to go to the 1930s or so when radio astronomy was started, basically. The major boost with radio astronomy came mostly because of the heavy development, technical development for developing the radar for the war, essentially. So that technology was then used to build the radio telescopes. So the first radio telescopes were built around that period, and they show that the radio sky is full of stars, which are not the same stars that we used to see with our eyes or with the optical telescopes, opening up a completely new window in the in astronomy, multi-wavelength astronomy, at least the two wavelengths, the radio and optical. Then we go to the 60s and rapid development. We had rockets at that time. Again, as a result of the war, rockets were invented. And some of those were used to go above the atmosphere to look out at the universe. And the reason for that is that the atmosphere absorbs X-rays, gamma rays, and also the far infrared or so. So if you want to look at the sky and those frequencies, you need to go above the atmosphere. The only way to do it is to mount some detector on top of the rocket or on a satellite. At the beginning, there was rockets. So that was the beginning of X-ray astronomy. So that's the beginning of my talk as well. But not only that, I opened up the window to the infrared, the UV, and gamma rays. Then, here very quickly, we go to the digital revolution. There's the computational astronomers, computer got much faster. And we had CCD sensors instead of photographic plates. Sensitivity got much better. We had supercomputers. A new era of the big data started. And that's basically the present. At the separation between present and future, we have what we call artificial intelligence. We don't really know. We only know that the potential of artificial intelligence is huge. We don't know what it will take us in astronomy, but we as an open universe, we want to maybe try to take advantage of that and make a little step into the future, making use of that. Okay, so let's focus on X-ray astronomy. As I said, the beginnings were in 1960, but before that, there was something happened. So we knew that X-rays from space people thought that there could be X-rays coming from space, from the universe in 1950. But again, the problem was the atmosphere. We need to go above the atmosphere. So when the technology allowed that, with the V2 rocket, they observed the X-rays in 1949, X-rays from our sun. So confirming that the sun at least emits X-ray, at least during flares. Then we go from sun to the rest of the universe. The idea of cosmic X-rays beyond the sun was only speculation, basically, until the 1960s. Then the 60s came with a major breakthrough made by Riccardo Giaccone, who is really the father of X-ray astronomy. He, at American Science and Engineering company that was on a mass having between Harvard and MIT, with Bruno Rossi, developed some payload, and which was a very simple payload with essentially Geiger counters, with not even constrained in the viewing angle. So they managed to get an aerobi rocket and they launched it. The reason why they got the money to build that, they were hoping to see X-rays from the moon. They didn't see any X-rays from the moon, but they discovered Scorpius X1. It was a very, very strong X-ray source, as I will show you in a moment. And so they demonstrated that there are sources of X-rays beyond the sun. They also discovered and there was a big controversy at the beginning, some diffuse emission, which was pervasive from everywhere. No matter where you looked, you saw some X-rays coming from the cosmos. At that time, they called it the X-ray background because it was a background radiation compared to the foreground, which was Scorpius X1. Okay, so then other rockets and balloon experiments identified our X-ray sources, including the Crowd Nebula and the galactic center. Then the 70s came, and they went from one rocket launch, which was going out of the atmosphere and stayed out maybe for a few minutes, to a satellite. A satellite can stay years observing. So the amount of time useful for observing the sky was dramatically increased. The first of this satellite was called Uhuru because it was launched by Riccardo Giaccone, by the way, again, from an Italian base in Malindi off the coast of Kenya. It was called Uhuru because it was launched on 12th of December of 1970, which was Uhuru Day in the local language, which means independence from the UK. It was the 5th anniversary or 7th anniversary or so of independence of Kenya. So everybody was going through this special day called Uhuru, and Riccardo Giaccone decided to call the satellite, which was launched into space that day, Uhuru. Ariane 5 was a similar satellite launched by the UK sometime after that. It was also launched from the San Marco spaceport in Malindi. And the reason why they did that, and they launched it in Malindi, in Kenya, and not from California, for instance, or in some American base, is because Malindi is at the equator. And the equatorial orbit, so if you launch from there, you can launch a satellite with a very low inclination compared to the equator, which has a very big advantage that the satellite doesn't go through an area of a very high background, the so-called South Atlantic anomaly. That's an area where particularly charged particles are concentrated by the magnetic field. So when your instruments go through that, it gets basically blinded by the enormous amount of background that is generated by those particles that are just there in the sky. So if you want to avoid that, the closer to the equator you go, the better it is. So that's why Malindi was chosen. And it was in a low Earth orbit. That means about 500 kilometers above the surface. So this is Riccardo. I call it Riccardo because everybody who's been working with him, from students to senior colleagues, they just called him Riccardo. Riccardo was Riccardo for everyone. And he was my boss when I was in the US in the 1980s. So I then received the Nobel Prize in Physics in 2002, around about 40 years after the discovery. The discovery was basically in this paper, it was announced in this paper, Physical Review Letters, Evidence for X-rays from Sources, note the S, not source, but sources outside the solar system. So they discovered SCO-X1, but they say also something else. So the crucial plot is this one on top. On the right, you see the payload, very simple. And the plot is this one. It shows the counting of the counter as a function of position as it was slewing around the sky. The black points are from another counter which was calibrated to the one exposed to the sky. It was not exposed to the sky, so it was measuring the internal electronic background. So the expected background is the black points, and the observed counts are the open points. You can see here that around 185 degrees or so, there was a very large excess. There was not the moon, because the moon was here, not quite at the maximum, but it was something else that they discovered, and it was clear that it was SCO-X1 when the other satellite was launched. You may notice that, okay, there is a very large excess here, but also if you look before and after, the amount of the counting of the open circles compared to the filled ones is always there's always a difference. And this was the so-called X-ray background. There was SCOX-1, a bright source, but also a diffuse emission from everywhere, no matter where you look, 0 degrees to 30 to 300 degrees, it was all the same. And that was puzzling for a long time, and essentially was the reason why Ricardo got the Nobel Prize, because explaining all of this, discovering and explaining the nature of the X-ray background. Okay, so then Uhuru came, a bunch of catalogs followed, and as you can see from one source, the red one, that was SCOX-1, many more sources were discovered during the 2 years of lifetime, more or less, of Uhuru. But then if you can, okay, so you can see that many of those sources are close to the galactic center or in the galactic plane, but there were also many sources above the plane. So these sources are from our galaxy, but also from the rest of the universe. Clearly, it's a major discovery. We went in the 1960s. It wasn't sure that even there was even one source of X-rays in the sky. Now we know there are hundreds of sources. So, but what are these sources? They are not normal stars. There are a few normal stars that can flare like a sun. Sometimes during the flare they can emit some X-rays. But most of these stars are very, very different, and the physics is completely different. Essentially, these are a degenerate star like a neutron star or a black hole with another star rotating around it. It's a binary system, and the very large gravitational field of the compact object attracts the matter of the wind of the other companion star. And when this wind of the matter falls onto the surface, it spirals around, it heats up a lot until it reaches temperatures that can generate X-rays. And all of this was completely unknown before. Also, the theory of the neutron star, the quantum mechanics, it was just theory before. Now it's there was a proof that such things really exist. So it's a complete revolution. This is a famous image from a so-called Rosa satellite, Röntgen satellite from Germany, which was launched in 1990 or so. It sort of gives you the history of X-ray astronomy. Riccardo Giacconi and Bruno Rossi wanted to, they said, we want to observe X-rays from the moon. This is the moon, which is, Riccardo Giacconi also discovered not the moon, but the X-ray background. Here we see that with the satellite that they had on board, not just a guided counter, but a real telescope. So you can focus radiation, which means that the sensitivity goes by a factor of 1,000 better. So we have a much more sensitive satellite than the early instruments built in the 60s. This is 30 years later. But this explains very well what happened during the first observation. The moon, it's really bright because it's hit by X-rays from the sun, and those X-rays are scattered. So you see the bright moon as well. But there is also the other side of the moon that doesn't receive the X-rays from the sun, so it's dark. You can still see some signal in there, but very little. That's the instrumental background. And you can see that the amount of red dots around the moon outside is much higher than what you see in the dark side of the moon, which means that the instrumental background is much lower than what you see around the sky. So that is the X-ray background. As you can see, it's very uniform, it's bright, and it exists. It's been observed. What it is, now we know that this is just the sum of many sources that could not be distinguish one from the other, which is confusion. So a lot of sources look like a diffuse emission. So this was a nice demonstration of what really happened during the first flight, discovery flight. Okay, then we go from there to the golden age of astronomy. So X-ray astronomy turned out to be extremely important. New physics, a lot of learning. So in the end of the 70s, another major thing happened. The Einstein Observatory was launched. That was my first satellite. I was with Ricardo working on Einstein in 1981. It was the first imaging X-ray telescope. So that means that it's not just a detector. There is a mirror that can focus X-rays, makes a very big difference, and that revolutionized X-ray astronomy. Then other missions followed. ExoSat was my main mission when I was working at ESA in Germany, then in Holland. ROSAT, that we've seen before, an image, ASCA from Japan. And then there was BeppoSAX. BeppoSAX was launched in 1996. And the major of the X-ray afterglow from the gamma ray burst. And I guess Giampiero Tagliaferri is speaking after me, who will speak a lot about gamma ray burst, simply because Swift was built after BeppoSAX. BeppoSAX, it was clever because it had some wide-field cameras, some detectors that had a very wide field, but the positioning was not very good. It was good enough to measure the position within a few minutes, but not very precise, like a few arc seconds. So they discovered with this instrument the gamma ray burst, and then people have been by hand repointing the satellites in a few hours, redoing all the mission operation that are necessary to repoint the satellite. It was very complicated. And then after a few hours, they pointed a more sensitive instrument with the focusing instrument, and they found that there was still some signal. There was some kind of afterglow, and that managed us to get a position which was much better. And at that point, it was known that those gamma ray bursts were coming from a distant galaxy. That was a major discovery. Okay, so in 1999, just after BeppoSAX, there was the Chandra X-ray Observatory, and then XMM Newton. Chandra is one of the great American observatories, had a beautiful, and it's still working, has a beautiful mirror with a very high precision focusing. XMM Newton, bigger, but with less capability of focusing. So one was mostly dedicated to imaging, the other one mostly dedicated to spectral analysis. And the interesting thing is that both Chandra and XMM Newton are still operational after so many years, 1999 to 2025, so 25 years or so. It's interesting because at the beginning, they were supposed to be lasting 3 to 5 years. After 25 years, they're still operational. There was also in the 1990s, there was also AstroSat launched, mostly for timing studies. Then the year 2000, 2010, Swift was launched in 2004, New Star in 2007 or 8 or something like that. Giampiero will be talking about Swift, which basically was designed after BeppoSAX with a wide-field camera called the BAT. It observes and detects a burst, and then automatically, instead of asking the mission planners to come work at 3 o'clock in the morning, it's all automatic on board. It shifts, it's Swift, moves and points the satellite, the X-ray telescope to observe, to continue the observation. New Star is the first hard X-ray satellite. That means that it's able to focus X-rays up to 70, 80 kV. All the others are stopped a few kV, like 5 between 5 or 10 kV. Maxi, he told me it didn't work for a long time. Maxi is still working, but it's mostly an X-ray monitor. Erosita then came in the 20s. Erosita was had a great promise of scanning the entire sky several times, 8 times. But then after 4 times, the war between Russia and Ukraine broke out, and the Germans decided to switch off the satellite. The satellite is still there, and that's why there's a circle, but the color is different because the satellite is still there, but it's not operational at the moment. It's just switched off. Hopefully, maybe one day they will resume operation. The China came into the business very heavily, and now it's producing a lot of interesting experiments on space, the lobster X-ray satellite. But then the XP and X-Pulsat opened a new window of the X-ray polarization, and this is just the beginning. Einstein probe with China is actually producing, detecting a lot of transient sources, and the SWAM and Eclair, which have been around for a long time, they're also similar to SWIFT. Einstein probe is more sensitive. So all of this enormous amount of data, some of which are completely open. So they are in Open Universe and Firmamento. In some others, we're still waiting. The interesting thing is that, for instance, the Erosita data, they decided to split the data from the German half of the sky and Russia, the other half of the sky. The German already published part of their data in their half of the sky. The Russian, they have not published yet. Maybe they will do that, but they say we don't have the resources to do the analysis and produce such a nice result. And catalogs that have been produced by Germany. And this comes back to some of the discussion we were making earlier today, that when you plan a satellite, you should make sure that the data is analyzed and published as part of the initial plan. Otherwise, you end up in this usual situation where you have a small team, they're very busy, they don't have the resources to publish the data, and at the moment the sky is only half filled by the German, and the other half is still waiting, and we don't know until when. Okay, so the X-ray astronomy therefore has transformed our understanding of high energy astrophysical processes. In the 60s, as I said, we didn't even know whether there was an high energy astronomy. Now we know, and we know it's very complex and very rich, and we've learned a lot of physics, extreme physics. So it's actually one of the ways to do to study physics in under very extreme conditions. So the key contributions: we discovered neutron stars before. With neutron stars, we had very strange things like black hole as well. They were studying theoretically, but nobody thought that we could see them. Now that we know hundreds or maybe thousands of them. We will see a few images later for each point here. We know that there are enormous clusters of galaxies, that is, structures with hundreds of thousands of galaxies that are gravitationally bound, and they have a very hot gas in the middle, which is trapped by the gravitational potential there, which is so hot that it emits X-rays by thermal Bremsstrahlung. We studied neutron stars and magnetars, supernova remnants after the explosion of a supernova. The matter is ejected, and the interaction between the very high speed matter with the local material generates X-rays. Then study the active galactic nuclei, both of those where there are jets pointing it towards us or not, but also non-jetted QSOs. Non-jetted QSOs are much more abundant. They have a supermassive black hole, and one of the big issues is to study how these supermassive black hole evolve across cosmic time. So X-ray astronomy is really probing the universe using the very interesting science and physics. So these are X-ray binaries. Essentially, you have a normal star here, which could be low mass or high mass. Then you have a black hole or a compact object there. That means an object which has a very enormous gravity. So this gravity attracts matter from the other one. This is a binary system, so one rotates around the other. And the matter falls to the hole or to the neutron star. It gets very hot and emits X-rays. In many cases, there could be also jets thrown out along the rotation axis of the compact object. This is a quasar. It's called quasar because it's a quasi-stellar object. This is a quasi-stellar object. This is a real star. You don't see much difference. That's why. However, the main difference was that this one is a radio source and these are not radio sources. But if you look at the optical image, they look really essentially the same, unless you look very deeply. If you have a better telescopes, then you can see there is a little jet there. And that's what makes a QSO also a quasar or a blazar. If the jet happens to be pointing in your direction, then the matter that is thrown out along this jet, which travels at the speed of light or almost at the speed of light, if it comes directly towards you, then it generates relativistic amplification, time construction, and a lot of funny things happen. And these are the blazars. It turns out that the blazars are very rare, but they are the most common sources in the gamma ray astronomy. So, and those are the most powerful cosmic accelerators known. As you can see, jets are fairly common. You have to take into account that the jet is aligned for megaparsecs or for very long distances, and the jets are visible in the X-ray. This is Chandra. Chandra, as I said before, has a very, very good resolution, so you can see the jet very well. This is a VLA, that's a radio, and this is HST in the optical. So jets are visible basically at all frequency where we have instruments that are sharp enough to detect them. This is another jet here of the giant galaxy M87, again with Chandra. This is instead something that this is the X-ray image of a galaxy of M31 Andromeda. There's a lot of sources. Again, these sources, like Uhuru showed, they are mostly binaries, compact binaries, and black holes, and so on. This is XMM. So this is Chandra. You see the quality of the optics. The points are very small. XMM. It's still good, but not quite as good as Chandra. This is a Swift. This is the image that we want to build the whole map during the cyclone. You may notice that there is a red source here, and the other source is a different color. You see this is the same from XMM, but also this is in Chandra. It's always red. It means it's a very soft source. There is a lot of photons at low energy, but no photons or very low photons at low energy. Okay, so this was a view of the Andromeda Galaxy, but only this part here. So you can see how different is the image from the optical viewpoint on the X-ray viewpoint. So the science is completely different. X-rays are also found and studied very well. Supernova remnants. This is a famous Cassiopeia A, Cas A. Again, Chandra, you see an enormous amount of detail because of the beautiful Chandra capability the Chandra mirror. This is the Crab Nebula, even more spectacular. You see all the structure and the jet there, fantastic image. And this is the image I started with. That's the Chandra Deep Field South. So we started, X-ray astronomy started hoping to detect the moon. Now we're going to the edge of the universe. So this is a 7 million second of the deepest observation done by Chandra in the so-called Chandra Deep Field South. There are thousands of sources here. So here we study really the edge of the universe, galaxies in the early universe emitting X-rays, QSOs, and so on. XMM also observed this field. XMM is the quality of the image is not as good as Chandra, so it would be confusion limited. Two different nearby sources would merge into a single source. However, XMM has a higher collecting area. It's a bigger telescope, and above a few kV, let's say above 5 kV, it is competitive, and it provides a complementary view of the deep universe at a higher energy, above 5 kV or so. So the two, the American and European satellites are complementary from this viewpoint. The other thing that, as I said, it was discovered galaxy clusters, not only systems where hundreds or thousands of galaxies are gravitationally bound, they also have very hot gas, very thin and very hot emitting X-rays. And this gives you a lot of information about the physics there. If you cannot distinguish the galaxies there, this image will make you change your mind. You see how many galaxies are in there. If you think that each one of those galaxy includes hundreds of millions of stars, you can see how many stars are in this enormous structure. Okay, then I finish with gamma ray burst because Giampiero will probably start from there. There was a puzzle that started with some satellites, the so-called Vela satellite, American satellite, checking the possible explosion by the Russians in the nuclear bombs in the atmosphere. So they had gamma ray detectors called Vela satellites. They instead discovered that there was some explosion in the cosmos. And then in the early 90s, BATSA was launched in the Compton Gamma Ray Observatory and discovered thousands of these. And you can see they are distributed completely randomly, I'm sorry, in the sky. Now, but nobody knew what they were, what these things are. And all it was known was that their distribution is very uniform. And that can happen if these sources are extremely close to us, so you don't see the galaxy because they are very close, you don't see the structure of the galaxy, or they are very far away. So you see the far universe, and you don't see the galaxy. And this mystery stayed there until Bepisax arrived. And this was the famous, actually, I did this image on 28th of February, 1997. One GRB was observed, and then with the wide field cameras, and then we repointing the satellites, and this is what we saw. There was some somewhat unexpected still radiation. There was some what was called the afterglow. The gamma ray bursts usually last a few seconds, maybe 1 minute, but then they disappear. After 4 hours, this was still there. And then this is February 28th, and then the picture on the right is 3 days later, and it was almost gone basically. So it's the source was there, but it was fading. And this is a typical gamma ray burst afterglow. So this image allowed us to measure precisely the position. So somebody looked with an optical telescope At this position, they discovered that this is a distant galaxy. So this solved the problem of the origin of gamma ray bursts. Gamma ray bursts are coming from distant galaxies rather than very nearby sources. If they are very distant and we still see them, they must be extremely powerful. In fact, they are the most powerful sources, transient sources in the universe. Okay, so my basically final thing, let me see, okay. It's just something that was said before, the data availability. We started in the X-ray data availability. We started in 1980s when I started my career. Basically, at that time, there was no archive. There was essentially a bunch of raw data. And the user community, as Ulysses was saying this morning, was only a few specialists from essentially from the hardware team. Only the people who actually built the instruments were able to analyze the data. And the data was essentially calibration data plus a user manual. The service from the who was running the satellite, the space agency essentially, that service to the user was just giving him the raw data by sending a magnetic tape by post. That was the status of things in 1980s. And then in the 1990s, we had the start of internet. People could transfer data more easily. Also, we had the instrument, mission public archives. After the disaster of Challenger, the mission that exploded, NASA said, well, after this disaster, we will not be able to send other satellites for a while. So you have to reuse data from previous missions. So the people started using mission data from previous missions. And they discovered that basically 90% of the data were not basically used or published. So it was a treasure. So a mission expert could do a lot of analysis using archival data. Also, this was possible to have multi-mission, have several missions after a while. So the number of people who could benefit of the data was from a few hundred, it went up to a few thousands of scientists. And then it came multi-messengers, so astronomers, but also astroparticle scientists got into the business. The data reached a level of science ready. That means you don't need to have to really do the deep analysis. Somebody else does it for you, and it's easy to use them for specialized for trained scientists. Okay, so but then we had ChatGPT, started with the AI era. So we have multidiscipline. Who benefits of the data is astronomers, astroparticle physics, any professional scientists that could use them. Now we are here talking about this, citizen scientists, maybe also normal scientists, the education sector. In the end, we started from a few hundred people to a few million potential people. And this is exactly what we want to do. Okay, so and one way of doing this, we'll be talking about this tomorrow. I've been talking about this yesterday as well, is Firmamento, which is a tool, part of the Open Universe, which allows you to get data in many different formats. And one of the tools that should offer the possibility to do some science to anyone. You can find it at this address, Firmamento NYUAD. As you can see here, we have a desert scene. It was done at New York University in Abu Dhabi. So NYUAD is New York University, Abu Dhabi, New York University, EDU. And with this, that's it. So thank you very much.
Thank you, Paulo. So I wonder if there are any questions in the audience or online. Let me check online, Paulo.
Yep.
on Zoom. No questions for Paulo? Okay, so let's thank then again, Paulo, and move on to Giampiero for the continuation of these two lectures on X-ray astronomy.
Hello, do you hear me? Yes,
Hi,
so.
hi, Giampiero. Welcome
Okay, thank you.
for being here.
Okay, I will start sharing my screen and see if it works.
Please.
Okay,
We see your screen.
okay, let me start the presentation. Okay, so now, as anticipated by Paolo, we'll give an overview on the Swift satellite that, as the title said, is a panchromatic gamma ray burst mission, but much more. Swift was just proposed with a very clear goal. It was to understand and study better the gamma ray burst. At that time, there was very excitement about the new results that were coming from WebPoSAC, as already introduced by Paolo. And therefore, the community strongly felt that it was necessary to have a mission that was going to exploit these sources that, as I will try to convince you, are quite unique sources. So the gamma ray bursts were discovered in the end of the 60s, early 70s, with a group of Vela satellites. They were launched just to make sure that no one was doing nuclear tests in the sky. And as soon after they will be launched, they realized that there was flashes of gamma ray coming from the sky. At the beginning, it was not clear. They've been enigmatic for tens of years. But the only thing that was clear, you can see here that when a gamma ray burst exploded, if you look at the left, the image, the gamma ray burst is outside in the whole universe in the gamma. So it is the most, it's a flash that is overwhelming all the rest of the sky. Just for a few seconds, you can see here the light curve is lasting about 5 or 6 seconds. There were hundreds of them discovered, and they were mysterious because the gamma burst monitor were able to locate them with an uncertainty of tens of degrees, and therefore people were never able to find where the sources that were in charge of these explosions. So for a long time, it was a discussion if it were galactic or extragalactic of origin. The first clue start coming with Compton Zero, which is about the BATS detector that detected hundreds of them. And you can see here in this figure, here is important on the x-axis that the time, the T90, is the time that the gamma ray burst is lasting. And you can see they are divided in two groups, so-called short and long gamma ray burst. And the dividing line is more or less around 2 seconds. So the short one lasting from a fraction of a second up to 2 or 3 seconds, while the long one normally are lasting a few tenths of seconds up to a few hundred of seconds. So the really breakthrough came with WebPoSAC. Paolo has already said a lot, so I did not spend time, but the uniqueness of WebPoSAC was that he had various instrument boards of gamma ray burst monitor that were able to detect the gamma ray burst. But then WebPoSAC was an Italian DAS satellite. He had also on board the two wide field cameras, which are coded mask, able to locate X-ray sources with an accuracy of 3, 4, 5 arc minutes. And so if a gamma ray burst detected by the gamma ray burst monitor was also in the field of view of the cameras that have a field of view of 40 degrees square, in that case, we could detect the X-ray counterpart with that accuracy, and then the satellite could be repointed and put in the X-ray telescope. There were 4 imaging telescopes on board that were able to locate sources with an arc-minute accuracy. And this repointing, we heard before, it can be done in time of few hours, and that's what it was done the first time in February 2008. You see this image, so a bright new X-ray source has been detected. A few days later, it faded away. But also, in this case, it was possible to have an arc-minute, more or less, accuracy position by WebPoSAC, and therefore it was also possible to find the optical counterpart. So, first breakthrough, there is X-ray counterpart associated to gamma ray burst, and there are also optical sources associated. Then, in the next few months, the second breakthrough was that it was possible to get also a spectrum, as Paolo said. This was approved that is cosmological, extragalactic in origin, and also this meant that the luminosity, the power that is intrinsic to these sources is huge, and as we heard, they are the most powerful explosion in the universe after the Big Bang. And also Bepp-Sachs, very important result was that the long gamma ray bursts were associated to the supernova 1bc. Only for very few of them, because we can see supernova up to a resolution of 0.5 with difficulty. With the current instrumentation, we cannot go back beyond that distance. While gamma ray bursts usually are a dire resolution above 1, 2, or 3, or even much more, I will show you. So only the very nearby gamma ray bursts, the long one, we established that they are associated with supernovae. But we didn't know at the time for the short because gamma ray burst short were not detected by Bepp-Sachs. So this was open question. So, in summary, the energy involved is 10 to 51, 10 to 54 ergs in total. The whole fluence are very enormous. The average of the detection is at 1, 2, which means that the universe was 10 gigayears light-year time. So we are talking about less than 10% of the age of the universe, around 3 to 2 gigayears compared to the almost 14 of nowadays. They are very relativistic, highly beam with a gamma factor other than 500, means that they are really a jet pointing toward us with an opening angle of a few degrees. And the variability of time of milliseconds. So here in these figures, you can see the modelization that what we think are the gamma ray bursts thanks to these results. There are two channels. With Bepp-Sachs, we explore the first one for the long one. We have a massive star of masses more than 8 solar masses. Then at the end of his life, the nucleus will collapse because there is no nuclear reaction able to sustain the gravity, and therefore a black hole or neutron star is formed in the center, and then there is a rebound and a blast wave, and a crystal disk is formed, and a jet is launched. Along the jet, we know that we are still inside the envelope of the star. You see, do you see my mouse? I hope so. So with my mouse, I'm pointing where is the borderline of the star, the envelope of the star.
Yes,
So inside the star, there is this jet that is excavating the envelope of the star. And there are blob of material and plasma ejected along. And when the two blob have different speed, they collide with each other. And here we have the gamma ray burst emission. So this is what we see in the gamma ray burst emission. So this has already been occurred when we see the gamma rays. And then when the jet go through the star, it come out from the star, then we start seeing the afterglow. So this is called internal and external emission of the gamma ray. Let me move this on top. Okay. The second channel, which was thought to be the channel for the short gamma ray burst, is that the coalescence of two compact objects, they rotate around each other, they lose momentum due to the gravitational wave, and then at the end they collapse. And so we have the merging, again a blast wave, disk accretion, and then from there on, the emission is more or less the same. But there are less material, less energetics, and therefore they last less, and they are short gamma ray bursts. So this is what we knew. Let me see if I can move this on top. No. I'm trying to move from the way okay. Okay, so that's what we knew from Bepp-Sachs. Power law, we detect a gamma ray burst, and then we have a whole of few hours, 6 to 8 hours was necessary, and then we have a power law decay of the flux. So the afterglow is quickly fading away. So the idea was, if we arrive on target much earlier, we have much more power, and we can study much better the physics of the gamma ray burst and the jet and the formation of black hole and neutron star. But also the sources are so bright that we can use as a beacon to illuminate the early universe and study the early universe in detail up to the very high redshift. And we also knew that they all have an X-ray counterpart, almost all of them. Therefore, it was important to have on board also an X-ray detector or a telescope. And here is the idea. This is just an example with quasar. This is a quasar redshift 3, so high redshift, but not extreme one. And you see the spectrum of the quasar, and then on the left side, after the Lyman alpha, this is the emission line in the quasar spectrum, is a redshift 3. You can see here that this is 1216, the Lyman alpha, which we show it here in 4700 angstrom because it's red shifted. But on the blue part, we don't see emission anymore from the quasar because everything is absorbed by the neutral hydrogen. Instead, we see a lot of absorption line. This is the quasar. The line is going toward us. Here we are on the left side. And here there is an intervening galaxy. Of this galaxy, we see the Lyman alpha, Lyman beta in absorption, and then there's the Lyman forest. These are all the material and clouds and galaxies that are along the light of sight, and therefore we can use this light to study the universe. With gamma ray burst, we gain a factor of even 100 or even 1000 in luminosity if we get there in the early minutes, and therefore that was the goal, one of the goals of SWIFT. So SWIFT was proposed to NASA and approved in October 1999. The proposal was approved for a flight in 2003. It was launched on November 20, 2004. So 5 years from the approval to the launch, which is by itself is an amazing, outstanding result. Normally, for a mission like this is a medium, which is 1.5 tons, is quite a large satellite. And to be developed in 5 years was almost a unique result. Thanks to the fact that a lot of hardware was already available, as we explained. But this is very, very, very outstanding result. The objective was to determine the origin of gamma ray burst, use gamma ray burst to probe the early universe, and also as a byproduct perform an X-ray survey because of the coded mass detector that was on board. But it was clear to everyone that with this capability, because it was able to repoint in very few, in less than a couple of minutes, it would have been very effective also for a lot of other sources that we will see. And these are the teams that are proposed, the Goddard Space Flight Center from NASA, US University, and UK and Italy that provided a relevant contribution. This is a picture, a graphic picture of the satellite. We have a coded mask, sensitive in the hard X-ray from 10 to 150 to 100 keV. It is locating gamma ray burst within a crucial few minutes. Then we have an X-ray telescope, an optical telescope, and most importantly, an autonomous repointing capability of the satellite that was detecting on board, automatically detecting a trigger, determining the position in less than 5 seconds, and if the position was safe, the satellite was autonomously repointing itself and putting the gamma ray burst within the field of view of the narrow field instrument in less than a couple of minutes. The record is 70 seconds, the record is 22 seconds, if I remember correctly. So this is an amazing result. This is still unique and parallel even nowadays. This is more than 20 years old satellite. And being able to repoint a 1.5 ton satellite in a few seconds and stabilize it, it will stabilize in just a few seconds. This is still, if you should consider XMM and chart that takes WebOSat would take in a few hours pointing, and even XMM and chart are the same. So this is a very unique result. This is a figure of the bar detector. You can see here at the end. This is the coded mask. So the hard X-ray goes through the coded mask. There are some more that you don't see by eye, but maybe in the previous picture you can see here. Here there are all where there is black. This is in lead, absorbing the other gamma rays. And then there are 32,768 pixels. Each pixel is one detector. So this has been putting together almost 33,000 detector with all the connections on. So this was an amazing achievement. And this was of the 3 detector was the instrument. This was the one that needed to be almost fully developed. While in the X-ray, we had the advantage that mirrors and detector were already available. In fact, Italy and UK were building the JETEX telescope. There were 2 of these X-ray telescopes that were supposed to fly on board of Spectrum is Gamma, which was a Soviet Union satellite that never flew because of a political issue that took more. If you remember, the Soviet Union then was divided, and at that time was delayed, and then it was finally cancelled. But we have developed 3 mirror modules. 2 were for JTX, and 1 was spare available for a new mission. In fact, this was the one that we proposed to use was for Swift, and actually then is the only one that flew up to now. And these were measured on the Panther, and so the properties of this mirror were able to satisfy the need of Swift, so they were already there available. The image quality is comparable to the one of XMM. In fact, the technology developed for this mirror, which is a follow-up from Beposat, it has been refined for this mirror, and then it has been used for the XMM mirror, and then for the Erosita mirror, and now also for the Einstein probe mirror. So it is a very successful, also for XP, so a very successful technology. The effective area is a factor of 10 less than XMM, so it has the same image quality, but XMM is a factor of 10 larger effective area. And this is the full telescope assembled. Here are the mirrors, this is the double reflectivity, then the X-ray are coming in the front. Here there is a door closed to keep clean the mirror, but in the sky the door will be open, mirror will go through the X-ray, double reflection, and at the end, after 3.5 meters, the focal length is 3.5 meters, there is the detector. Here you see the camera. Also, the camera was developed for JTX by the Leicester University in UK, and this is a new camera made by the Leicester University together with the Penn State University, but the CCD is the one from JTX, and most of the electronic is the same, although some parts have been made new in the US. So that was the reason why we are able in less than 3 years to have already an X-ray telescope of this capability, because the hardware was already being fully developed. And this is the image quality. You can see the scanning the image. One important thing is that the field of view has a very good image quality, good in terms of XMM, not like Chand, of course. The half energy width I told you before is 15 arcsecond. Half energy width is the dimension of the circle in which 50% of the photo of a point like source will land. So a point like source you see is somewhat extended. It's not an optical image. But you see that it's flat, the half energy width all over the field of view. And therefore, this is also quite good if you want to observe, for instance, extended object or crowded field, because the PSF, in the case of Chandler, for instance, the PSF is extremely good on axis, but off axis is even worse than ours, and XMM also. So this telescope has to be able to cope with a source that goes from 0.2 to 15 crab. When we point a gamma ray burst counterpart at the beginning, they are extremely bright. They can be even 10 times brighter than a crab, which is one of the brightest sources in the sky. So for HRT, this source will provide 10,000 or 15,000 counts per second. 0.2, of course, is providing much less. So the telescope needs to cope with sources that go from a milligrab to tens of crab. And this can be done by different operating modes. The most important for the gamma ray burst is imaging mode. So this is used at the beginning. The X-ray telescope is used like just imaging, like in the optical, no energy information. And this is the trigger automatically on board. It will detect the source position. You see the flux here go from 0.1 crab to 100 crab. And this is the capability of the telescope by fully automatic to get a position better than 2 arcseconds. You can see here we are down to 1 arcsecond where we are around the crab, and then we are also above 10 crabs. At this point, the source is so bright that it switches. In the first part, it's accumulating image every 2.5 seconds. If it is brighter, it goes every 0.1 second. And this is what we need. It is used at the beginning to do the full automatic analysis. The third instrument is UVOT, an optical ultraviolet telescope. Once again, this was almost ready when we proposed Swift, because it is a copy of the one that is on board XMM. There are some differences, but very minor. Most of the hardware was already available, and this has been developed by the MSSL in UK, which are also responsible for the optical model on XMM. And this is the filter wheel, and this telescope is a multi-band photometer. You can see the 3 filters in the optical and 3 filters in the ultraviolet. It has also spectroscopic capability, but with low efficiency, so for only very bright sources, this can be done. So This now you see the satellite with the two telescopes mounted. This is the X-ray telescope. Here on top is the mirror. On the bottom of the satellite is the detector. So there is this tube is 3.5 meters going through the. And here you see now the full telescope, the full satellite with also bat mounted. Here you see the two telescopes, and here there are 3 people and one there, just to give you the dimension of this satellite. This is in the clean room at Cape Canaveral, ready for launch, which occurred in November 20, as I told you. And in fact, the satellite was supposed to stay in sky at least 2 years, plus 2 years, but now it's running since more than 20 years, like before Paolo told you for Chandra and XMM. And in fact, last week we had a meeting in Florence just celebrating the operation of 20 years, where we are comparing the results of SWIFT with other satellites that are in the meantime taking over, like SWAM, which is a satellite from China and France, which has properties very similar to the one from SWIFT. Then there's the Einstein probe that is serving the sky in X-ray and looking for variable sources. So they are taking over to SWIFT when SWIFT will stop working. There are some of the capability, but some they will not have it. And you see there are more than 200 people that took part to this meeting. So this is the observing scenario. This is what was in the proposal. So the image that you see here are just simulation. The principle that we suggested that we proposed in the proposal was, but we detect a source. This is done on board. In less than 10 seconds, but we provide a 4-minute position and set it immediately on ground. So people can already observe with the telescope after 4 minutes, after a few seconds with this accuracy. In the meantime, the satellite will repoint and put the source in the field of view of the X-ray telescope that in less than 100 seconds will provide an X-ray position better than 5 arc seconds. And then in the next 5 minutes, also a new image will be sent on ground. So this is what we proposed, and this was what we achieved. So this is now a real data for this gamma ray burst detected in 2009, but detect the source with an accuracy better than 2-3 arc minutes normally. Then SWIFT is pointed in 1 or 2 minutes normally, and it detects a source with an accuracy of 2 arc seconds, so much better than the 5 arc second requested. And then finally there is the U-Root image, and you see the box of bath of the one of XRT. Within the bath error box, even if it is just 2 arc minutes, then there are various optical sources, but within XRT, which is 1 arc or 2 arc second, then there is just one optical counterpart. So this makes the follow-up on ground much faster and much easier. So these were what we were aiming for to fill the gap. We completely filled the gap, but we were expecting to find a power law going all the back way. But normally, when you open a new window, you always find surprises. So the light curve are much more complicated. Already the first few light curves, you see these are detected in January to March of 2005. So we start observing gamma ray burst in 24th of December of 2004, because we had to wait a few months before being able to switch on the instrument. And so the satellite was so quick that we already with XRT detected the gamma ray burst. So we are seeing the queue of the gamma ray burst emissions, which is fading very quickly. Then there is sort of flattening. It was totally unexpected. You see here, there is a steep decay, a flattening. Here we have an orbit because SWIFT is on Earth orbit, 90-minute orbit. Therefore, all sources are occulted by the Earth, and therefore we have to move away from another source and then come back after the source is visible again. And we see here the flat component, which is not unexpected, and then sort of going steeper and then steeper again. It is normally probably the jet break that was already been observed with Beposat. So the light curve is much more complex. And in fact, not only that, but we see also flaring still going on. Here is 200 seconds after the burst. And in this case, we had a huge flare. Again, we are just in the first few months of observation, May of 2005. And you see that this huge flare to order of magnitude, 1,000 seconds after the burst. So this means that the central engine is working much longer than expected, not just a few tenths of seconds, but hours, even days. You can see here there is another flare almost 1 day after the burst. So there is much more richness, and this allows people to study much more detail and understanding better the central engine. So I'm showing here just an overall plot of the light curves, the various component. The blue one is the one detected by BAT, and then the other color, the one detected by XRT. So here they have the prompt emission, the fast decaying of the prompt emission, and still going on activity. The green one are the one we expect it to be, but then there are, which are just about 1/3 of the gamma ray burst behave like that. The other have a lot of activity going on even at a later time and flaring, and then sort of flattening here is more confused and depending, and then going and decaying following a power law. Another goal that we saw, one of the goals was to study light curve at the beginning, and it was fully achieved. Also, one of the goals was to study gamma ray burst at very high redshift and give them immediately the position and not allowed to study the early universe. The first one again was this is 2005 in September. We find the redshift 6.3. Remember that we, as I told you before, we normally gamma ray burst were detected at redshift 1 or 2. Before with Bepossac, we swiftly increased, the average was above 2, but this was the really first gamma ray burst and very aggressive. Nowadays, we see that we have burst with the James Webb telescope of galaxy at redshift 9, even 10, but on that day, this redshift was very uncommon, but this is different. We are not just seeing a galaxy, we are seeing a star that is dying, so it went through the whole life and exploded when the universe was very young. In this case, the universe was less than 1 gigayears old. And not only that, but we can also study in detail, you see here the spectrum that was taken in this case 3.5 days. So we are at the beginning of the mission. Astronomers were not used to be so fast. Nowadays we are pointing with the 8 telescope in a few minutes, and so we have a much better signal, but this is the first one, it was the historic one. Still, you can see it dying here. Your silicon, oxygen, carbon, and this allowed to study in detail the composition of the chemical composition of the host galaxy, of the clouds where the gamma ray burst exploded, but not only that, also the property of the gas, the dimension, the temperature, and so on. So we do real physics inside the galaxy, which is so aggressive. And here you can see the Lyman alpha, that is, you only see the right part of the Lyman alpha, then everything here is absorbed by the intervening gas. This is because we are still in the universe that is what's called the dark ages. You can see here you see the age of the universe. Here we are 17 million, so just after the Big Bang. Here we are 10, this is the redshift. The redshift 10, we are alpha gigayears. And here we still, the universe was dominated by neutral hydrogen gas. And therefore and then the first galaxies start forming here, but the light cannot go through because they are completely absorbed by the gas. But the gases start to be ionized by these sources. And until we are here around the redshift of 5, we are full reionization complete. So this is the so-called reionization era. And this now is the universe we are used to see nowadays, back 2 years. So we with gamma ray burst are going to look inside this galaxy to check what is going on in that galaxy. You see the redshift, the spectroscopic redshift record order for Swift is Z equal 8.2. We are also redshift 9.4, but it's photometric, so I not put it here. And then we have various at redshift lower. And just to show you some example here, these are all gamma ray burst at redshift 7 to 6. Let's take this one. You see here we have much better enriched spectrum and with much more line. And you see that if you go at redshift below 5, you don't see almost anything blue world of the Lyman alpha. Everything is absorbed. To want to see Lyman forest, you have to go here afterward. And you see better here than you see alpha of the Lyman alpha, of the wing, the right wing, and then everything is absorbed. There is no photon at all from blue world of this line. And here you can see also, you see, the total absorption is the green line. The purple line is the one due to the neutral hydrogen, which is almost everything. The red one is the one absorbed by the host galaxy. And therefore, we are able to determine how much neutral is still inside that galaxy. So we can have a look at the evolution of the absorption around redshift between 8 and 6. After 6, everything is transparent at that point. But we can really study how the ionization is occurring and who is responsible for that. But of course, we need many more of these gamma ray bursts are digressive to do that in more detail, but just to show the powerful of this object. Then another goal of Swift was to determine the counterpart of short gamma ray bursts. Remember, Sachs didn't see them. And again, in May of 2005, the first shot was detected. An X-ray counterpart was found, but was much weaker than the normal counterpart for the long one. So this was the first result. And that's the reason why the error box is of 9 arc second. We only had a few counts from the X-ray band. No optical detection of the counterpart. So this is a very bright elliptical galaxy, probably is the core galaxy of a cluster of galaxies. And the gamma ray burst was at the outskirts, was here. This is the X-ray position, and determined even better than with Chandra. And there is no optical counterpart, but the result is that these are associated with an elliptical old galaxy. So already this one is completely different than what we have seen for long gamma ray bursts. Now we have a lot of more than 60 short gamma ray bursts with those galaxies detected thanks to Swift. And all of them, the gamma ray bursts you see sometimes are located outside the Earth galaxy or in the outskirts of the Earth galaxy. And they are all old galaxies. Some of them are still star forming, but the short is always never associated to the star forming region, but to another area of the galaxy. And this is corroborate the idea that they are coming from a different channel, as I told you before. We think that short gamma ray bursts are associated to the coalitions of, we have two compact objects spiraling around each other. Before merging, it takes about 1 billion of years, or giga years, before the two objects are able to collapse with each other, to merge. And therefore, at that point, these are not associated to star forming region anymore. These are old objects, while the long gamma ray bursts are associated to young objects, stars that last for a few 100 million years. In this case, we have giga years. And another important stuff is that these are the sources that people thought were responsible for the creation of the heavy element, the radioactive element. Remember that inside the star, we can only produce up to the iron, the peak of iron. Then nuclear reactions are not able to produce heavy elements. So where are the lead, gold, platinum, or uranium, all this kind of material coming from a different channel? And one of the possibilities was the so-called kilonovae. After the merging here, we have a dense material that are ejected, a lot of neutron and proton that can reach and put together. And so we have the so-called R process forming very heavy elements. And this was finally proven, was amazing results, thanks to the association of a gamma ray burst with this gravitational wave event that was detected in August 2017 by LIGO Virgo. By LIGO, while Virgo was not detected, but it was useful to provide the position. And this object was detected, and then Fermi integral found the gamma ray burst counterpart. So this was due the LIGO Virgo, the gravitational wave detector, are able to determine what kind of collapsing objects are merging. In this case, were two neutron stars. The two neutron stars merged, and they were associated to this short gamma ray burst. It is quite weak, as you can see, but this was detected because these objects are very nearby. We can only see nearby objects nowadays with this gamma gravitational wave detector. In particular, at that time was just the first version of this detector. Now they've been improved, they are more sensitive. But still, we were able to detect the counterpart. Swift did not see the gamma ray burst counterpart because it was pointing somewhere else. But it immediately did the follow-up and was able to detect the ultraviolet counterpart. So this is the galaxy. You see the UV detected by very bright source, then it disappears after a few weeks. And here you see zooming in a very bright UV. So and this is the spectrum of the associated kilonovae. You see it was very blue at the beginning, and then the peak moved and get redder and redder and redder. This was quite unusual. In fact, people were expecting kilonovae, but thought they to be red. With this, we prove there are red and blue kilonovae, and this element, this line corresponds to various lanthanide element that was a smoking gun, proving that there was a kilonova associated with the merging of two compact objects and also forming this heavy element. I think this is a very outstanding results of course multi-massive gravitational wave, electromagnetic spectrum, and that was the result. Another breakthrough that came from Swift, in this case, was associated with the fact that it was able for the first time to receive the shock breakout of a supernova, or detecting a supernova in the act of exploding. This is a very long gamma ray burst that you see. It lasted 10,000 seconds. It's huge long, but there's also thermal emission associated, which is not easy to disentangle for the non-thermal emission due to the gamma ray burst. The non-thermal is the gamma ray burst, the thermal is due to the supernova. If you remember, there is the envelope around the supernova, which is the stars. In the core of the star is forming a black hole or a neutron star. There is a blast wave, and then this is putting out. And when the blast wave emerging outside the star is breaking the envelope of the star, this is called the shock breakout. We were never able to show it before, because normally when we see a supernova, this already occurred. In this case, thanks to the fact that we were pointing to a gamma ray burst, we point a gamma ray burst, this was a nearby, we were able to see the associated supernova, and we see the shock breakout. In particular, this color-like curve, the ultraviolet and optical taken with UV, and you see that the yellow is the most UV, and it's peaking around here. Then the other UV, that is redder and redder, the peak is coming afterward, and this is explained by the modelization of the shock breakout. And as I said, this was the first time that we see it, but Swift, and this actually a plot that showing this again is all the spectrum of the supernova taken from optical telescope, of course, and this is various example of supernovae associated to the long gamma ray burst. Once again, remember, we can only do this for the very nearby, the one that is below 0.5, which there are not many. But let's go back to the shock breakout, because Swift detected a second shock breakout. In this case, there is no gamma ray burst involved there. This is a galaxy that was observed by Alicia Soderberg, was observing this galaxy because in this galaxy there were various supernovae that exploded recently. So she was studying supernova remnant with the XRT telescope and UVOT. And while she was observing, another supernova exploded. We were very lucky. You see here the light curve. The satellite just arrived on target just before the explosion. We see here now a very clean, soft X-ray light curve, because, again, this is just the supernova. There is no gamma ray burst. And we see very clearly the burst coming out from the supernova. So this is the shock breakout of a normal supernova, and then it rapidly fades away, because the X-ray supernova it just occurs after a few days. In the beginning, there is no X-ray, only during the shock breakout. And we were very lucky to detect, again, this shock breakout, thanks to all these various capabilities of Swift. So we had now almost 20 years of observation of gamma ray burst, but even nowadays, sometimes Swift is providing amazing results. In the 22, we have this, it's called the monster gamma ray burst. It's called the BOAT, which is the brightest of all time. It's obliged that we expect to have one of these every 10,000 of gamma ray burst. Only one is so bright. But even more peculiar is the fact that this was very nearby, 0.1. So you expect to have one of these bursts, if our Logano guess is correct, one every 1,000 years. So we were extremely lucky to see it. And this burst was so powerful that almost all satellites were blinded, were overflowed by flash. So the detector were for a few times were blind because there were too many photons. And it was observed by all, both all satellites, but all telescope on ground. Everyone was pointing to this object. And one of important results you can see is the blue one. So these are just the few brightest, and this is almost 1,000 times brighter than the other one. Okay. And but in the case of Swift, the unique results were that thanks to very brightness, we could see very well, study very well a dust echo. A dust echo, what you're seeing here is the absorption due to an intervening cloud in our own galaxy. So in our own galaxy, there is a dust of cloud. It is along the line of sight toward the gamma ray burst. When the X-ray photons are arriving on these clouds, they are scattered out, and so it's all forming a ring because the photons are scattering, enlarging, getting as by the time passed by. But because the gamma ray burst is not just a single impulse, it's just more than one. There are a lot of bursts coming from the gamma ray burst. And so we see more than one circle expanding. And this allows to study in detail the properties of the dust in our own galaxy, the dimension, the size of the grain, and also the density and so on. This was not the first dust echo detected by Swift. There are about 10 of them, I think, if I remember correctly, but this is, of course, the most spectacular one. Here there are both XRT data, but also XMM. You see the observation last 12 days. The first few days are XRT because it's very bright or is enough XRT, and then XMM is taking over. Therefore, that's why a very detailed study can be done. Another very recent important example is this gamma ray burst for two reasons. First of all, I told you the boat was the brightest of all time, you expect one every 1,000 years, but then 5 months later, the second brightest of time was detected. But this is not intrinsically so powerful. This is the uniqueness is the fact that it's so near. Look, 0.06 in resi. So the flux is very high. And it can be studied in detail. And then we repointed the James Webb telescope to look for the supernovae because we knew that at this rest we can study very well the supernovae. But in the optical, we couldn't not see it because there was not a supernovae. But again, there was a kilonova. Kilonova has a factor 1,000 times normally weaker than the supernova 1bc. So that's why we couldn't see it. Only thanks to the James Webb telescope we were able to see it. And we see the kilonova. This is quite elusive. This is recognized by the lines that are again due to lanthanide element, or the heavy element. This is a clearly smoking gun for a kilonova. But this was a long gamma ray burst. So this is the peculiarity of the results. So in some long gamma ray burst, we are not have a supernova, but we have a kilonova. So there are still some physics to be understand in the precursor and what is the source associated to gamma ray burst. So to summarize, Swift up to now has detected more than 1,600 gamma ray bursts with Arc minute position, 80% that were repointed with Arc second position, and 70% are repointed, so almost all of them are reporting less than 300 seconds, and 400 of them we have the redshift determined from follow-up on ground. So this is a large and homogeneous sample that people can use to study in detail gamma ray burst for times to come as well. So this is a very good database that people can exploit just for gamma ray burst. But Swift was just, we said, a machine for discovery machines, or discover very interesting objects that are not gamma ray burst. I just report a few examples. In this case, this at the beginning was classified as a gamma ray burst, but after one day it was clear that it was not a gamma ray burst. Look at the variability. We have 3 orders of magnitude variability lasting for a few days. Then it starts decaying. This was a tidal disruption event. This is a supermassive black hole of 10 to 6, 10 to 7 solar masses in the center of this galaxy. A star went too much nearby to the black hole, and so it was tidally disrupted. The risk was formed. But this is just the uniqueness, because nowadays we have seen various of these tidal disruption events. There are tens of them studied in the optical, UV, X-ray, thanks to Rosita and other Einstein probe is detecting them as well. The uniqueness is that here we are seeing not just a risk accretion, but a new jet has formed and launched. So we are seeing the launching of a relativistic jet in an extragalactic object. So this is actually the birth of a blazar. And in fact, the emission has been modeled with a synchronous Compton emission, normally used in the blazar. Normally in blazar, we see 2 peaks, one due to synchrotron, one due to the Compton. In this case, we just seeing only the synchrotron part, and there is no pair. And in fact, it is what we said, particle star, but magnetically dominated jet, not particle dominated jet in this case. But once again, it's a unique case where we have seen a jet while it was just starting, pointing toward us. But in all these years, there is a strong evolution in the way people are using Swift. Thanks to this uniqueness and its capability of fast repointing, if you look at these two cases, here you see that in 2005, at the beginning, almost half of the time Swift was spending to study gamma ray burst, 17% of the time for calibration, and almost 20% to observe other objects. 18% that is the South Atlantic anomaly, because we are in low orbit, we go through a South Atlantic anomaly, and therefore we cannot observe because the background is too high. Now look at this is 21, but this is exactly the same nowadays. The evolution is now flat. 70% of the time we are observing other objects, not burst. Only 9% we are looking burst, and only 4% for calibration, because now we know very well the instrumentation. We just need to check time to time, but not to do long calibration campaign. This doesn't mean that we are not observing burst anymore. Every gamma ray burst detected by Swift is observed and followed for a few days. Also, gamma ray bursts detected by other objects like Fermi or nowadays Swarm or Einstein probe are followed with Swift because they want to have a better position. The point is that in the olden days, we were observing gamma ray bursts for days, weeks, and even months. We followed a gamma ray burst for almost 1 year. But then it was clear that after the first few days, it's just a boring power loss, and there is no point to keep observing them for a long time. And so we can save time for do other stuff. And here, look at these figures. Here, the target of opportunity they are performed every year. You can see that it's rapidly increasing, and then since 2018, 2019, we are about here, and which means that every day Swift is doing 4 to 5 targets of opportunity. So observations that were not foreseen and that were requested by the community, they are approved. And this can be done just with a couple of people managing the mock. We have only 3 or 4 people managing a satellite 20 hours a day, 7 days a week. Thanks to the flexibility that their satellite can almost work autonomously. So when we have a target of opportunity, you just check on ground that is okay, but then you send it up on the computer on board, the position, the coordinate, the exposure time you want, and then the satellite readjusts itself the scheduling. And by doing this, Swift is observing almost 25 sources every day, because being in low Earth orbit, it is obscured by the Earth after a few thousand seconds. So instead of waiting, like for instance, Rosat or Bepossac was doing like that, when they are obscured, they were waiting the source coming out of the dark side part of the Earth and pointing the same, staying on the same object. Swift is always moving 3 or 4 times, 5 times, 7 times per orbit. 20 times a day. It's always looking to maximize the exposure time. When one source is obscured, you point another one, and then another one, and then another one within an orbit. And then it goes back to the previous source, the next orbit, and so on. So by now, Swift has made more than 700,000 views. It's outperforming by order of magnitude all the other satellites. No one is jumping in the sky like Swift. So this is the uniqueness of the capability of this satellite. It's something that even Swarm and even Einstein probe cannot do. So I think we will miss where Swift is not in the sky anymore. This is another example. Swift is also very good in doing monitoring, and for that we have a huge database of sources that can be used. And I think it's a richness, probably Paolo will show this in the next days, is one of the most interesting database, I would think. Here is observation of a few Schiffer galaxies, and doing reverberation, intensity of accretion disk reverberation mapping by cross-correlating light curve taken in X-ray, in the various filter, in the UV and the optical, and we can monitoring how the variability propagates through the various band. And this in the UV gives very consistent results in agreement with a thin accretion disk, while in the X-ray it's more complicated. The story is not so clear because there is not just the disk emission at that point, but there is also a corona that is illuminating the disk, and therefore there is an interplay. In some sources, X-ray are preceding, in some other sources are the UV preceding the X-ray, and therefore that is more not so clear cut. Here is just showing this example. I took this from an old presentation of Paolo. Here is just monitoring various blazars. This is the spectrum taken with XRT. The database is much more rich. This was taken 10 years ago, or actually 12 years ago, but now there are many more. So you can see that these sources are very variable, and you can compare the status. This is the spectral energy distribution of this source. It goes from the radio up to the gamma ray, even the TeV band in some cases. And you see the variability that you can observe. This is the extremely peak VLAC, so the cyclotron peak in the X-rays. There are two examples, a lot of variability. This is in the immediate one with XRT, we are sampling the turning between synchrotron and compton emission. And in this case, instead, is low peak for C273 with X-ray, with XRT, we are just detecting the starting of the compton. But you can see that there are a lot of status doing multi-wavelength variability, comparing data with from Swift, from Fermi, and optical, and so on. Gives you a lot of capability to observe this kind of variable stars. So, just a few minutes more, and then I finish. I would say up to here, I'm talking about variable sky, and I think the Swift is really the reference point up to now in the last 10 or so years for the time domain astronomy. Everyone that wants to do observation is always asking for Swift as well. Also, larger satellites like NuSTAR, like XMM, like XP, or ground-based observation, TeV observation, they're always looking for simultaneous Swift observation, which normally is giving me up. Another peculiarity of Swift is that the XRT telescope has a very low background. So for instance, we are talking here about a cluster of galaxies, which are extended emission. Therefore, one thing that the better way to study them is to use XMM and use Chandra, which is true because I have large field of view and very good effective area, much higher than XRT. But if you want to study the low surface brightness object, then XRT is much better. You need to have a long exposure time, but it has a much lower background. And this is a campaign for Stefano Andreoni, his colleague, for instance, who have spent the last 10 years to show that X-ray clusters selected in X-ray are biasing because you can only select those that are very bright surface in the center. You lose the ones that are more extended, low surface brightness, are the one showing here. Here there is the mass of the cluster, here the luminosity, and the others sitting here. And they claim that this is the real distribution of cluster, and these are the ones they observe with XRT. And while these ones are the ones that are selected in the optical or with the sonar, the Doppler effect. They are selecting instead just using the velocity of galaxies, and there is a clumping of galaxies with the same velocity. They said here there is a new cluster, and they're going to observe in X-ray. I don't have time to spend here, but just look at this cluster. This is observed with XMM, very bright in the center, but all the rest is dominated by the background in XMM. And the same is true for Chandra. Even if Chandra has a very good PSF, it is due to the orbit. We are low orbit, so we are protected by the Earth atmosphere, the external one. And you can see here there is almost no background. All you see here are photons from this cluster that goes out much further on than what you can study. With XMM, you can study right here, and then you start losing out. And look here, you can still detect the photon coming from the cluster, plus, of course, pointed sources. And finally, byproduct is also, this was already the proposal. There are almost 1,000 sources by now, 900 and something, detected in the hard X-ray with BAT, and these are dominated by AGN, and 1/3 of them are so-called the obscured AGN. So this is probably the largest sample of obscured AGN that are available nowadays. And just to conclude, because I think my time is almost over, I think Swift is the reason of the big success is designed as a mission for the rapid follow-up, has proven to be highly flexible, dynamic to allow observation of virtually any type of astronomical sources. This is thanks to the autonomous response of the satellite, and also to the flexibility of the Swift team is managing the satellite, allowing for having a lot of targets opportunity every day. Normally, even with ESO, which is a ground-based telescope, we have to supply for DDT to the director, and you can have an answer in 1 or 2 days, and then you can start observing the next day. Here, we have answer in hours. If it is extremely urgent, it can be reported the same day. Otherwise, in 1 or 2 days, you know that your source is going to be observed. You just apply online, and this, I think, is the strong capability of Swift. And I think with this, I will stop.
Thanks, Giampiero. I see some messages online. Let me see if or on Zoom chat. No, it's not a question. So is there any question in the audience? Yes.
Hello, Professor. Thank you so much for the presentation. I really like it. I got two questions. The first is that I saw that the SwiftBet catalog contains a lot of AGNs. I would like to know if it also contains some starburst galaxies. And the second question is that I understood that the BET detects a candidate for gamma ray bursts, and it triggers the telescope to point in the direction of the candidate of a gamma ray burst. So I would like to know if this BET has a limited field of view. So where do you point the BET to try to detect some candidate for gamma ray bursts?
Okay. So I answer the second question first. So BART has a very extremely large field of view, 1 pi, so 1/4 of the sky every time is observed by BART, while XRT and U-Boat have a very small field of view. BART is pointing almost nowadays is pointing where the is looking where the satellite is pointing, because we are pointing every time. If there is not a new gamma ray burst, we are pointing. We are scheduling sources. We are pointing blazar. We are pointing binary system. We are pointing starburst galaxy, whatever. And while we are pointing, BART is observing 1/4 of the sky around that position, which is huge, you know. And because gamma ray bursts explode randomly, we don't know where they explode, so it doesn't matter where you're pointing for them. And so when BART detected the object, it calculated the position and then it immediately repoint with the computer on board. And so the slew can take, I don't know, 30 seconds or 300 seconds, depending how far away is in the sky respect where you're pointing now. Because if you're lucky, BART is detecting gamma ray burst not far away where you're pointing, and therefore we are there in just a few seconds. Or you can detect it very far away, because again, you're looking at a quarter of the sky and can be much further away. The first question was about the starburst in the. I think there are a few of them, but you know, there are. I'm not sure by heart, but I think about 30 or 40% of the sources are still to be identified, because some of them are really well known. They are the usual hard X-ray sources already known, because the limit is about now I think is around 1.1 milligrab or so, between 1 milligrab and 0.1 milligrab, 10 to minus 11, 5, 10 to minus 12 air per square centimeter per second. So they are quite bright, but some of them are still to be find a counterpart. So a few starbursts are detected, but not many. I would say 5 of 10. There is a paper recently published on by the God of People. I don't remember now the first author, but I can send you the detail of this of the paper with all the various identification that they have done so far.
Okay, thank you so much.
I don't know if there is any other question. If not, we are a bit over time, but I want to jump in.
Let me just say one word that Giampiero didn't say. All the data of Swift are immediately public to everyone, and that was a great success. The team is a competitor of the rest of the world, and is also a servant to the world. And this configuration turned out to be extremely successful.
Yes, I forgot to say, well, you're right. You can even check in the database and go there and see the observation that Swift is doing now. When it's downloaded, it is automatically analyzed by the pipeline and then in a few hours, it's already available in the database to everyone. To the people that has requested, but to the whole community.
And so let me just to close pick up on this, Giampiero. So what do you think that initiatives, or how do you see initiatives like Open Universe contributing to the mission of such observatories and experiments? And of course, the aim is to reach a larger public, but I'd like to hear from you what you think of this, the impact and where these initiatives should work.
I think the two things are probably very well matched. I think the Open Universe, Swift is a perfect mission to aim at, because the richness of the database in terms of data that are there, optical, UV, X-ray, soft X-ray imaging, hard X-ray, we coded mask, or and there is available the software for analyze it, which is more very user-friendly. The BAT was the most complicated one, but now in the last few years, people have realized that it was necessary to have full exploiting to make a software that was, easy to be used by large community, not just the expert. So I think the two are really matching in a perfect way, and Open Universe is one way to find new results in that data, because you're open to new people. Might be sometimes they have even crazy idea and can find things that other people didn't find it.
Great. Thank you very much, Giampiero, and thanks again to Paolo. So I think this really sets the basis of what is behind the science and the data we are going to be working with over the next days. So thank you very much for your time.
Okay. Bye. Bye.
Bye. And now we have lunch and come back at 2 p.m.
Hi, Ada.
Hi. Hello. Can you hear me?
Yes, I can hear you.
I can hear the room with a echo. Is that
Yes, let me try to fix it.
Okay, thank you. Okay, hi. I'm going to try to share my screen. Let's see. Can you see the slides? Okay, seems good. Okay, I'm going to see if I can remove
Hi, Ada, are you there?
Hi,
Okay.
hello.
So welcome everyone to to the first part of the afternoon section, where we will have Ada Nebo from the Virtual Observatory to talk about Virtual Observatory, and there will be a demonstration after the talk. You have the floor. I mean, maybe it's better if you stop between what you're talking about and the actual hands-on. So if there is an actual break in your presentation, so we can gather questions and whatever from the
Yes,
participants.
so I've structured so hi everyone. So my name is Ada Nevot, and I'm working in France at the Observatory of Strasbourg. Yeah, so I have structured my presentation so that there is a part in which I will be presenting slides and things, and then I will move on to a little bit more of a hands-on session with some videos, and sometimes we will go to the browser and so on and so forth. So I plan to make some breaks here and there to allow for questions and discussion. Okay, so and also don't hesitate to stop me at any time that you consider it necessary. So no trouble with that. So now I'm gonna share my screen, and I think we can start. So I will turn my monitor off and my video there. So you see my screen correctly?
Yes, yes, we do.
Very good. Okay. So, so first of all, thank you. Thanks a lot for inviting me here to present a little bit about the Virtual Observatory. Okay. And this is the structure of my presentation. So I will talk a little bit about the astronomical data, its diversity, the Virtual Observatory, the vision of what the Virtual Observatory is, and then a bit of some examples of tools and services, and a practical session around images in particular. Okay. So astronomical data. If I had to define astronomical data with one word, it would be heterogeneous. So there are many different types of data in astronomy. So we have images such as this one. So here we have an image in which you can see so it's an infrared image taken by a satellite, by TUMAS. And in the center of the image, there is something like a blur. It's a galaxy. And then, but the important part of this image is a little supernova that is barely visible there. And you might not see it in the infrared, and therefore the need of combining data with other missions. So we have images such as this one, but we also have a spectra, which is shown here. So here we have the flux of a star as a function of its wavelength. And with this spectra, we can determine the type of object that we are observing. In this particular case, it's a carbon star. And by comparing with some models, we can estimate the temperature, the gravity, and other parameters. We also have light curves. So in this particular case, we have 3 different light curves of the same object in 3 different phases of its evolution. So it's binary, it's orbiting, and there are things going on in this object. And by analyzing the variations of the flux with time, we can constrain what is currently happening in this binary, where it's going through outburst and decline and quiescence. So these are information that is very informative about the object and its evolution. So other type of data that we can have, and this we see it more and more often, are data cubes. So data cubes can combine spectral and imaging capabilities at the same time. So we can have that through simulations, but also through instruments attached to telescopes. So these are like basic type of data, but we have other data that is very valuable, and that is publications. So publications have embedded in the text information about objects in astronomy. And this is really valuable information because it might tell us a lot about maybe not a million objects in one go, but about objects that have been studied in a lot of detail. And so collecting that information in astronomy is extremely valuable. And then embedded within these articles or through compilation of survey data, we can have catalogs and tables. So here, a catalog composed of HD numbers. So those are the numbers of stars, their magnitude, for instance, colors, extinction, rotation of the star, temperature of the star, and as many physical parameters as one can imagine. And so tabular data is part of the landscape of astronomical data. So as I say, heterogeneous, various heterogeneous data. And also, one of the things related to astronomical data when we think about data in astronomy is the amounts of data that we get today. So we have a very large volume of data, and we're producing more and more each day. So we have data that can come from simulations, such as the image on the left, which comes from the Millennium simulation, and producing terabytes of information. And we can also have telescopes producing or capturing images, spectra, and so on, either from satellite missions or ground-based telescopes. And we do this in any wavelength that you can imagine. So we observe objects from gamma rays to radio, and also we combine information on the electromagnetic spectrum with particle physics, so with neutrino and gravitational wave information as well. So, so why do we do this? So why do we observe in many different wavelengths and collect data such heterogeneous and so on? Well, it's to learn the physics about objects, right? So here I have on the left side, I've selected a few surveys that we collect data from, covering from the UV, so the ultraviolet light, all the way to the radio emission. So these are just a few among the ones that are out there, but I've picked this because I know them very well. So from the UV with GALEX, X-ray and UV from XMM, infrared from TUMAS and ALLWISE, and radio NVSS, FIRST, Akari, optical SDSS, SkyMapper, PanSTARRS, Gaia, APAS. And so why am I mentioning all these surveys? Because we collect photometry from many different bands. And why do we do that? Because by comparing the photometry that we can observe for these objects, we can learn about the physics of an object. And this is now, so we move to the image that I put on the right. So we have what it looks like a star surrounded by some diffuse emission. And actually, by collecting photometry of that object, what we can see in the bottom panel is the spectral energy distribution, so the photometric points of that object at different wavebands. And in order to explain each individual measurement of the flux, we need three components. So we need a star, that's the blue line in the spectrum. We need also to have dust around it, okay? And then, so that's the green part of the spectrum. And then we need a third component that is only emitted if there is a high magnetic field in this star. This is related to synchrotron emission. And so it is very important to combine all the information that we can have for studying correctly and, or not correctly, but like to compile as much information as we can in order to know what the physics behind an object is. And so to highlight what this means, if we applied it to another image, so I think this is a very good one because it explains the issue that we would have if we only would observe things, for instance, in the visible or only in the infrared. So imagine that you're observing an elephant, but you don't know that you're actually looking at an elephant, and that a scientist is only looking, for instance, at the tail of the elephant. It might conclude that actually it is a rope. And another scientist that is looking, for instance, at a leg might conclude that it's actually a tree. But only if you actually have all the pieces of the puzzle, you can learn that it's actually an elephant. So multi-wavelength astronomy and multi-messenger astronomy is about this. It's about getting the different pieces of the puzzle to understand the whole picture. So, okay, so, so the different pieces of the puzzle is the different types of data. And so this data is distributed by the astronomical archives. So there are dedicated archives that distribute the data. And so here I picked up a few examples. So we have NED that collects data for galaxies. We have the CDS in Strasbourg, where I work, where initially it was it had 3 services: Sinbad, Vizier, and Aladdin, and we will see them later. So I'm not going to tell you much about this now. We have ISA for the space missions in Europe. We have IRSA, we have MAS, we have ESO, ADS for publications, and so on and so forth. So these are archives distributed worldwide to distribute data to the users. Now, the users. So what do the users need? The users want to do their science. So the astronomers want to do the science, and in order to do that, they need to firstly find data, access it, and analyze it. So we have different archives out there. So imagine you want to find some data, but you just don't know where it is. So the first problem a user can be encountered with is the data discovery. So the question is, how can I find data archives that have the data that I'm actually looking for? The second one would be, okay, now I found the archive, I've identified it, but I'm only interested in a part of it. So, and parts of it that are fulfilling certain conditions. Can I do that? Can I actually discover that data? And then I want to access the data and maybe transfer it to my computer or work with it online or whatever it is that you want, but you want to access your data. And then you want to analyze it. And for analysis, now is where the harder part starts because, well, for images, different telescopes, different cameras, they might have different pixel sizes, pixel scales, orientations in the sky. So combining information can be difficult. For a spectra, same story. So for instance, an astronomer working in the high energy domain will work typically in kilo electron volts, while if you're working on the radio, you will work on gigahertz. And so we need to have conversions. We need to carry the units of the things that we're talking about. So different units in both wavelength and flux are typically available. So we need to put everything into a same system so that to facilitate the work of the user, the astronomer. And for photometry, well, as I mentioned before, we can have different photometric points in different bandwidths. So where is the information about the filters, the detectors, the telescopes? What are the different photometric points so that I can convert from magnitudes to fluxes and vice versa? So these are typical problems that we are all encountered with, and that a common ground can be found. So to solve those issues. And then for catalogs, the same story. So there can be lots of different measurements with not only different units, but also with different column names. We can call the V magnitude VMAG or V, or you name it. We can invent many names for the same concept. And so we also need to bring that to a common ground. And so ideally, a user would query a service and then say, I want to find photometry, I want to find a spectroscopy, asks to the service through a tool, and the service responds easily, here it is, work with it. And so that is exactly the idea of the virtual observatory. So the archives, so they gather together and they discuss about what can be standardized. And we came up with the concepts that are needed in order to say your data is fair, your data is findable, it's accessible, it's interoperable, and it is reusable. And so archives make the link between the user and the data to facilitate its life. So, so how is that done? Through conversations, through workshops, through meeting, through discussions about what needs to be standardized. And this is an international work. So it's done through the International Virtual Observatory Alliance that actually sets the standards for enabling the so-called interoperability. And so then to sum a little bit up, what is the virtual observatory? Well, it's the ecosystem that is formed by archives, tools that communicate to each other, and so that allows the user to find, access, interoperate, reuse data, and so that they can carry out their science. So it is not a tool, it's a way of doing things. Okay, it's not a single thing. It's not a single portal. It's way of doing things. And so for establishing those standards, there is the IVOA, the International Virtual Observatory Alliance. Okay, so standards, what are we talking about? Well, there are many different types of standards, okay? And each standard defines the minimum common information to share services, to share between the services and the tools, okay? And so there can be standards for tables, for images, for spectra, and so on and so forth. So, okay. So I don't know if to this point there are any questions. So now I'm going to talk a little bit about services. If there are any questions, please just ask. Feel free.
Nope, so far.
Okay, very good. So now, so I'm going to show some services that have actually integrated the VO. Okay, so we could call them VO services. So the CDS services, there are three main services that I'm going to talk about. One of them is Simbad. So Simbad allows us to retrieve information about astronomical objects. And so how does this work? Well, you might know the name of an object. Here, for instance, the name of this object is WR110, but it's not the only name it has. It has many others. So these are called synonyms. And so there is a dictionary to keep the names of the different names of the same object, okay? And so either way, you put the name of the object or you put the coordinates, and then you have access to a set of fundamental data around this object. Coordinates in different systems. There can be information on the type of star in this or type of object. In this case, is a Wolf-Rayet star. So that is a massive star with very strong winds. And you have the spectral type, the magnetism, and you have a little image that allows you to visualize not only the object, but also its surrounding. And this can be extremely important, for instance, when we're at the telescope and we point our telescope to the object, and we want to be sure that we're observing the correct object. Also, we capture information on all the bibliography around this object. So any paper that mentions this object will be contained in this database. So there will be a link to the publication in particular. Another service that we have is Visier. So Visier is a database that contains tables and catalogs. So tables, as the one that I showed at the very beginning, that can be small, okay, 50 lines, or you can have catalogs with billion objects. So, and they are accessible. You can access them through the web browser, but you can also ask, so you can also access through Python or other ways. So there's always programmatic access to this data as well. So here is just a few examples of the links to particular catalogs, such as Gaia DR3 or Glimpse, containing photometry, and then at the bottom is a little capture of a catalog around the Large Magellanic Clouds and the Small Magellanic Cloud observed by ARAC. And so then for each individual object, you can have a lot of different information. And then we have another tool, which we will see more today. So it's Aladdin. And Aladdin allows us to visualize the sky. So it allows for visualization not only of images, but also to overlap catalogs, and then to access images that might be stored locally in Strasbourg, but not only. So we have different nodes worldwide, and so different archives are all connected, making this interoperable system. And we will see a little bit how that works in practice. So here we have 4 images displayed around the interacting galaxy M51. And you can see it in the optical, in the infrared, in the X-rays, and then in the far infrared, I believe it is. And so you can see that images can have different resolution, and that not all the objects emit in all the wavelengths. Okay, so you can see those obvious things from investigating the images in the same region of the sky. But there are other tools, other virtual observatory tools. There are many, and I'm just showing you a few of them that I found really interesting for my research in particular. So, for instance, the Spanish Virtual Observatory has the VOSTA service, which actually allows you to collect the photometric data around a source, a single source, or a catalog of sources, and then fit stellar atmosphere models and even an extra dust component to the stars, and then derive temperatures and gravity for those stars by fit of the stellar atmosphere models. And so like this, we can learn about the evolutionary status of the stars. So I find this tool very interesting. And there is the TopCat tool as well. It allows you to access data also in other places through different tabular protocols that have been developed in the virtual observatory, and fast manipulation of tables. So you can visualize, but you can also interact with other services. So this one is also very powerful. And so, I mean, there are a lot of different tools out there. I am a little bit biased. I always show the ones that I use the most, but there are very wonderful tools out there. So also something that I want to mention is that the virtual observatory started about 20 years ago, around the early 2000s. And since then, we have seen that actually it is an increasing tool, so as to say, that is being used, and it's cited in publications, and people are really doing science thanks to the tools and the services that are created. And just to put a little bit of things out there, here we see a history of the usage of the tools in papers, so in publications, TopCat, Aladdin, and VOSA. And independent on the numbers, what we do see is like the increasing number of publications that uses those services. And I think this is very promising, and it also reflects that it's a healthy system. It's not it's still producing a lot of good science. It's enabling science. So that's that I think it's a very good thing to see. And so if we look at some of the papers that use the virtual observatory, we can see that, for instance, so I just picked a few, okay? So this one here, the viewing angle in AGN, spectral energy distribution models, data-driven analysis. And so this is interesting because it's objects that are really far out, okay? And we can analyze them using, in this particular case, they used the CDS service and NED, and then the collection of a spectral energy distribution that was analyzed. And then on the other extreme, so very far objects, active galactic nuclei, and very nearby hot subdwarf stars detected within our galaxy can also be analyzed through the virtual observatory. And this one in particular even carries the virtual observatory name in the title. And some of these papers have made it all the way to becoming tutorials that are online. So for instance, here, the second one, discovery of brown dwarfs, mining TUMAS and SLOA databases. So we've worked so as to the story that the paper tells, put it into a tutorial, and it's online and it's accessible to everyone. And so I think it's a very good way of showing the power of these tools and the services and what it allows us to do when we're able to reproduce the results of a paper, and the other way around when we are actually just using the tools to allow us to do the science, not just to reproduce it, but to actually make discoveries. Okay, so I don't know if I've gone too fast in this part. I hope everything was clear. If you have any questions, I see that in the chat there was something, but I'm not sure there was a question.
There was nothing.
Okay, very good.
Let me check
So then-
again. Okay. No, we don't have any questions on the chat, but do we have any questions so far from the audience before we go to the hands-on demonstration of Ada? I actually have one, Ada.
Yes,
You
please.
mentioned that there are lots of tools, and at least in my experience with CDS and Aladdin, it's sometimes a bit hard to find documentation on how to use them. Is there a centralized place where you can find all of these things?
Okay, so that's a good question. For what it is, the CDS services, we have transformed our website and now it's centralized. So we have all the tutorials there, and so each of the individual service has its own documentation. So Aladdin, for instance, has a full documentation that is more than 100 pages, if I remember correctly, and we have it even translated into several languages. So the most recent one is the French and the English versions, and you should be able to find it through the website. But can you see my screen here?
Yes, we do.
So here, if you just go to the CDS, here you can find the different services up there, Sinbad, Vizier, Aladdin, okay? And then if you click through them, then so you have the presentation of the service and the user's guide, okay? So here you can go through the user guide and how to use the service, how to optimize the queries. For Vizier, it would be the same. You would also have its own dedicated page. And for Aladdin, there's a lot of information as well. Now, so here I'm talking about the CDS services alone, but I also showed TopCat and I also showed the Spanish VO. And so each individual service has its own documentation. And we have worked to making pointers through a single portal, but it's very complicated to keep it up to date. So I think like the for the CDS, this would be the reference.
Okay, thanks. Or any more
Yes.
questions? So if not, you can go on to your hands-on demonstration of VO.
Okay, very good. So I think so we could talk more about the aspects here on the VO and what it does, but I think like the cool part is what you can do with it. So and I'm going to concentrate on images. So images, 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 and then catalogs as well, because that's gives us a lot of information. So HIPS. So HIPS stands for Hierarchical Progressive Survey, okay? And so this is a format that the IVOA has invented to put all the images in the same type of format and allow the user to visualize the sky, okay, a multi-wavelength sky, to visualize it, to zoom in, zoom out, search for data, and analyze it in very innovative ways. So each of these images here is covering one wavelength. So it's from radio all the way to gamma ray. And we're now going to see what I mean by innovative ways. So, but before that, so what is the principle? The principle is the following. So the idea is that as you move in through the data, if you're zoomed out on an image, you're certainly not interested on the tiny details. So you don't need a full resolution image when you're zoomed out. But when you're zooming in, you want to start to see the details. So this is exactly what this type of format allows you to do. So the principle is the more you zoom on a particular area, the more details are showing up. So we're all used to using Google Maps. So this is pretty much the same concept, but on the sky. And so it is possible to do, so this type of structure, okay, it's possible to do it with the images, but it's also possible to do it with catalogs. So we just need to define how to hierarchize the information. So, and images is the resolution. In catalogs, one can say, I just want to see the most, the brightest sources, and then zoom in and start to see the fainter ones. So that's a choice. So, okay. So let's open Aladdin. So here, okay. And now, so just to be sure that the bandwidth was going to be okay, I decided to make a video, but I'm going to stop. So here, what did I just do? I opened Aladdin and I just clicked on DSS, so Digital Sky Survey, to access optical image, okay? And immediately an image appeared on a certain particular region of the sky. Here we can see, so this is the tool Aladdin, okay? The desktop tool. And so here to the left, we can see the available data. So about 40,000 types of data. So some of them, about 600, are images, and most of them are catalogs, okay? And so here, this collection is, so catalogs is mostly dominated by Visier, but it is connected to different databases worldwide. So now by clicking, an image appeared in the optical and the DSS, and here in the right, we can see the stack. Okay, so here there will be more and more things appearing along the way. So let's have a look. So now I have this image and I'm zooming out. And so now okay. I zoom out and I can see the entire sky. I'm changing the frame, so I'm putting it in the galactic frame. And here we have the galactic plane, and that's around the galactic center where I'm zooming in, and it's in the optical. Okay. So you see that some tiles are starting to appear, and you see how, as I zoom in, it's kind of like querying the service and the tiles are being downloaded and accessed. So the more I zoom in, the higher resolution I get in. And if I zoom out, again, I go to low resolution. So now I'm going to query for other data. So now I'm going to visualize Tumas in the infrared. Okay, and I'm clicking progressive, okay? Okay, there, progressive, because I want to progressive view. There you go. So that's the same location of the sky in the infrared. I zoom out, and again, you see that how the tiles are appearing and disappearing. That is the latency of when it's downloading the correct tiles at the correct resolution. So it's only accessing what is in the view. There you go. And now what I did is, so I'm playing with the opacity of the two surveys. Okay, I'm going to redo that. So that's the infrared. And I moved the little, the opacity slider, and I can overlay the infrared and the optical images. And I can visualize the sky at other wavelengths. I'm going to query in the ultraviolet, the GALEX mission. And now this is a particular mission because, okay, let's put that back in. So here, you saw that the other ones, they were covering the entire sky, but GALEX doesn't, okay? GALEX is not an all sky survey, but it's actually targeting specific regions, specific targets, and it has a relatively small field of view in comparison to the other two missions. And so that's why we see these patches that it covered, okay? So it didn't cover the entire sky. And also, you see that here you have this red, and in some other regions, you will see more like bluish. It's because it has two filters, and we combine them to create a color image. And not all the filters observed or detected the same sources at the same time. So there is a little bit of not overlapping regions there. So that's why we see here this red image that is dominated by a single filter. Now, I'm zooming out. just exploring a little bit the sky, and you see the three surveys are moving in, right? They move at the same to the same location. So I can control with the mouse the location of the view at the same time, the view of the three different surveys at the same time. So now I'm going to add a fourth survey. So I'm going to select an X-ray survey, Chandra. And again, I'm going to do the progressive access to the survey. So these hips. And the same story as before. So Chandra is a pointed observatory. So it observes certain regions of the sky. So those are those dots or those squares that we see here. That is what Chandra observed. And now, again, I'm going to play a little bit. Okay, that's very difficult to see Chandra on top of the optical image. But for that, what I can do is split the panel in 4, and I can drag and drop the different surveys, image surveys, into these panels. So now what I did is I have the optical, the infrared, the UV, and the X-rays. And so I'm going to go to a specific object in the sky, and I clicked here. I don't know if you saw it. I clicked here. That went a little bit fast, but I clicked here in match so that all the panels are synchronized. So I'm observing exactly the same region of the sky. Okay. And so I typed in the command line M51, and it moved in all of the panels to the position of M51. So here we have it. And so then we can zoom in and we can see how stars dominate the optical, and how in the X-rays, what we see are interacting objects that are, we don't typically see the stars in the X-rays. And now I'm going to load a catalog of sources. And okay, I'm not going to load the Hubble, but I'm going to load the Pan-STARRS catalog, okay? In progressive version as well. So the more I zoom, the more I will see the sources. So it overlaid the position of the sources in that catalog. So every single point is a source in the catalog, corresponds to one line in the catalog of Pan-STARRS. And I can do the same with Gaia, progressive. Okay, I'm loading it. So Gaia DR3, another optical catalog that contains parallaxes of stars. And I can select objects. And here at the very bottom, I have access to tabular data, okay? So I can see the values, okay, here. So the Gaia name, the coordinates of the object, the source identifier, and so on and so forth, as many columns as the catalog actually has. And if I click on a source, the image on the top moves to that location in the sky. And it does that in the 4 panels at the same time. So that allows for a quick visualization of different objects in the sky at different wavelengths, and which might have had different parameters. I could do selection of these objects, right? And here I'm showing I can do histograms in this little panel, and so on and so forth. Okay. So,
Ada, sorry, since the video is over, I have a question here from the audience.
Very good. Yeah.
Questions. Can you, if you click on a point, if I want to know a point in the sky map, what it is. It's just a click, right? To get the name and to know in which catalog it is.
So if you want to know, so what I did now, I loaded a specific catalogs, okay? If you want to know what the object is, you have the identifier in Gaia, for instance. So an object can have different names in different catalogs, okay? Now, if what you want to know is, has this been studied? Is this in the Simbad database? Is that your question?
Well, I'm not, if, I don't know, you had some images in X-ray and I found a hotspot. I don't know if you can go back. This is a video or
Yeah,
where?
this is a video. I can also reproduce it. I mean, I was just afraid that maybe I was going to have some issues with the
Yeah,
internet.
you can go back in this video of, I don't know, 1 minute. Okay, there, suppose we are there. And
Okay.
I want to know what is the bright objects on the top right, for example. Yeah.
Yes. Mhm. So there are different ways. So you could query this tag here for catalogs around the source.
Okay.
Okay. Or what I would do, because this is a bright source, so I'm pretty sure that it has been studied with a lot of detail. I would just leave the mouse there, hover it, okay, and then it will automatically connect with the Simbad database. Let me show you, okay? Can you see my screen here?
Yes.
Okay. So I'm just launching Aladdin. And I'm just going to do the same. Click DSS. There you go. So now zoom out and I think it was this star. So did you see that? So I just clicked and then it appeared like a magnifier that is called here study. You see this is in green. That means that I am allowed to study that object. And what it does is actually it connects to the Simbad database. And then a name appears, a type, a magnitude, and bibliography by Simbad. So now I can click here and it automatically sends me to the Simbad database.
Okay.
And then, yes?
No, okay, finish and then I have another question.
No, you can go ahead. I think this is it's good. There is a interaction, so please go ahead, ask your question. Yeah.
Okay, now this one you answer and it's great. The other one maybe more complex. You showed us many tools for images, but I work in gamma ray astronomy and we are a lot interested in time variation of sources. Is there any tool around that you know can make light curves or really study the temporal variation, the temporal evolution of sources that you know?
Okay, yes. So that's a very good question. So for the variation of sources, if you have a light curve of an object and that has been published, so we have two things. We have, on the one hand, we have access to the data through the archives, okay? And then you have tools to analyze the data. So there is a tool called Period 04, which understands the formats of the VO. Okay, so if you found your light curve, you can send it to that tool, and then you can do a period search or things like this, and phase fold. So analyze the light curve. Okay. Now, period search is good when you have a certain regular variability. If there is no regular variability, imagine you have a supernova explosion, you know that it's a burst and then a decline. So you have an explosion followed by you have an explosion. And so for that, we don't have a specific tool in the VO for analyzing that, but to access the data, you can find it through the different archives. I'm not sure if I am answering your question. I can show some examples, but there is not we don't have a tool as this one for visualization that would work with all the different light curves that are out there.
Okay, Ada, there's another question here too.
Yes.
Hi, Ada. My name's Jamie. What I'm seeing on Aladdin is it looks like you're using an LLM system. Is that correct?
No, no, this is not an LLM system, actually.
LLM.
This is connected databases. Mm.
Yeah, but it appears like on the right-hand side, you have the editor where you would put all of your, sorry, the left-hand side, the editor, where you would put all of your information. Then you have the mapping zone in the center, which you're using for an image. And on the right-hand side, you could theoretically, if you're using AI, then that would be your robot data and your agent. So when going back to Michele's question, what you could do is overlay several LLM user frames and utilize AI to access all of the different maps that you may want to integrate into a certain image or data recording.
Okay. So yeah, so the let's put it this way. This is a tool that is specialized for visualization of images, but it allows you also to play with catalogs and to visualize. For instance, here you see down here.
Yeah.
This is the spectral energy distribution of that particular source. But this is querying another service and is bringing the data from that service all the way here. So imagine now that you have a light curve. You could imagine that as long as the service would have tagged that information as being a light curve, the only information that you need is, okay, this is the light curve and this is the information that I'm going to transmit. Flux over time. And then you can and you wouldn't need more than that.
Well, you could always put that onto another screen or monitor, couldn't you?
Yeah, exactly. I mean that so you could do this here, or you can even do it down here. So there is so here, for instance, okay. So here now I could plot things. So down here I can just plot things. And if I have a catalog here, for instance, earlier, okay. I mean, I just typed this, but I'm going to, I don't know, imagine, I don't know how many, okay, 140,000. So let's imagine that, okay. Okay, there are none in this view of you, but, okay, now there are some in the view. Now it's green, so it means there are some. Okay. Okay, so now I have this data here, okay? So you see the position of appeared here. So that's because I have coordinates in the catalog, and so that's possible. Now here I have tabular data at the very bottom, and you see this little widget there, it has a time. And because it has a time, I know that there is a temporal component there. So I'm just gonna drag and drop. And you see what happened now. It opened a window and it's asking me, what do you want to plot against what? So what is the x-axis and what is the y-axis? And so now I can just say, okay, well, for the x-axis, I want, and here I have a period. I don't know. Okay, I'm eyeballing this part, and then here I'm going to say the B magnitude. And then I'm going to apply that and close. And if I was lucky, well, there you go. So it plots things, okay, here is not the light curve of the object, which is what I would have loved to have, but it's that individual information that is in this catalog, okay?
It's fantastic. It certainly answered my question.
And now imagine, okay, I'm gonna go further a little bit. Imagine that this here, which is called source, it would be called light curve. And that this link would be the light curve. I would click on it and it would send it here. It's not the case in this particular case, but that's where we're going.
Brilliant. Does that answer your question? Because what I would do, I would cheat, to be perfectly honest with you. I tend to use a lot of AI, and I like to work across multiple monitors. So where you're using the Welcome to Aladdin area there, I would have that the whole chatbot, and I would make an agent that I basically, rather than having to mess around with all of these different bits and pieces of information that you've got, I would talk to my robot. I would make a robot basically and say, look, I want you every time I press this or I ask that question, I want you to provide, say,
Yeah. So I think that the difficulty here would be like in the so I agree that is a possibility here, like interacting with the AI right here. And what we do now is like we have this thing here, right? The filter, and then here we can query, and it could be here as well, right? It could be like, okay, give me the light curves. Which light curves are available here, or which spectra is available for these sources in the field of view, or you know, that sort of thing. So it would be like pre-selecting already the interesting columns that I'm looking for. No.
Yeah.
No.
And knowing how to read the parameters as well.
No. No.
Brilliant. Thank you. Thank you, Ed. I'll pass you back.
Any other questions so far? So we have one more, Ada.
Okay.
Ayada, thank you very much for such inspiring presentation. My name is Aldo. I would like to know what is the data we are looking for? Are those just images, or is it a point cloud or some other measurements, maybe? Thank you.
Okay. So yes, so we have a lot of images here available. So about a collection of more than 600 different type of images. So images done by different surveys, different telescopes. And we have a collection of about more than 20,000 catalogs, okay? And so to show you what I mean by catalog, the best way is to go to VCR, okay? So here, this is where the majority of the catalogs come from, okay? So we have 26,000 available catalogs in VCR. And so what does a catalog mean? So here, let's put Gaia DR3, find. Okay, so when I typed Gaia DR3, what did the database do? It understood Gaia, it understood DR3, it didn't take them as a whole, so it's showing me anything that contains Gaia, Gaia DR1, DR2, distances to Gaia, and so on and so forth. And then it might also, later on, we might see other catalogs that contain the word DR3, okay? It could be that DR stands for data release. So there are many surveys that create data releases, and there might be other DR3, so SLOAN DR3 or XMM DR3, and so on and so forth, okay? So here, what I have is a title, a paper, so that is a publication, a little visualization of what it goes in the sky, so where the sources are, and here, the interesting part, which is the catalog. And so the catalog, what is a catalog? A catalog can be a table or lots of tables, okay? And so here, for instance, if I go to this table in particular, this table of this catalog contains all those information, all those columns, okay? So I could select them all the columns, because I want to see all the columns of this catalog, and I'm going to limit to 50 objects so that I don't query for a billion sources right now. And I can submit, and there you go. And so what do we have here? We have coordinates with a positional error. We have the solution ID, the source ID, some epoch, so the time, the epoch of the coordinates, the parallax, which in some cases is empty, and oops, and many other columns that in some cases is empty, but in a lot of them is not. Okay, and so here you have magnitudes, you have positions and galactic coordinates, and so on and so forth. Now, this information is available through VCR, through Aladdin for fast visualization of the data. Okay? But what Aladdin is doing is connecting to this service behind. And how is it doing it? Well, because this service is registered as part of the virtual observatory. And then a virtual observatory tool can query that. You see what I mean? Does that answer your question?
Yes, it does. And we have another question.
Okay, yes.
Hello. Oh, this is the first time that I'm seeing some software like that. Is this like a HeoPix image or something like that? And is it possible to like download the data and work with and like plot this image in HeoPix using C++ or Python, something, or it's like too complicated?
No, it is not too complicated. So this is totally based on HealPix. Okay, so the tessellation of the sphere in a HealPix way. And what is behind the scenes is the way that files are structured. So you have the files, they belong to directories, and those directories just contain the different cells at the different resolutions. And so because of that, you can use any library that can deal with HealPix. And so in Python, you can visualize this. And actually, you have Aladdin Lite, which is for an IPy Aladdin, which is for integration into Jupyter notebooks and Python. So I don't know if you're using that type of thing, but here, okay, I was going to show you a little bit later, but I think it's the right moment, is the same tool, okay, for doing this, but on the web browser. And so, okay, wait a second, let me just, Aladdin hips, okay. So here, I can zoom out, I can zoom in, I can visualize Tumas, for instance. Whoops. I can change to other projections. Oops, maybe. Can you see it better now? I can move on around the galaxy. So there you go. So now that's the galactic center. And here it's overlaid the Simbad database. So here, if I click, I see the Simbad information of that object. And if I zoom more, then I have more resolution and so on and so forth. You see how objects appeared on the fly? And this is not a video. I'm doing this really like now on the fly. So it's querying the database and in a HealPix, in a HIPS format. Oops, again, let me close this. So you have, so this HIPS in action, but what I wanted, Aladdin, okay. So I've been showing how to access data using the desktop application. What I just showed you right now is the Aladdin Lite, so that you can put on your browser. And if you're working with Jupyter notebooks, then you can use IPy Aladdin. And you can follow here examples and how to integrate it. Does that answer the question?
Yes, it does. Do we have, okay, we have one more.
Okay. Yes.
There's Jamie again. I'm very sorry.
No worries. Yes.
A lot of people that I work with, they've just started discovering things like stellarium. Now, the things that you guys are doing are just light years ahead of stellarium. But what might be fun, I don't know about any of you guys, but what might be fun as a beginning thing to try and encourage more people to look at the sorts of things that you guys are doing is to understand how we can maybe integrate parts of what you're doing with a program as easy to run as Stellarium. They can, oh look, Cygnus, and
Oh.
understand what's happening in that constellation, for example. Is that possible?
Yes, so actually, so I don't want to say anything wrong here. I'm not the person that is in charge of making the connection with the stellarium, but we do have projections, for instance, in planetaria, using the software of even the planetaria. So just the other day, we had a session here for the public in which we used the projection. So we made modifications to the so that it can be projected correctly into a planetarium. And I am sure that Pierre Fernic and Thomas Boch, who are the developers behind all this, uh, um, they would answer much better than me, and they would tell you, oh yes, but it has been integrated into a planetarium, or a stellarium, sorry, or you know. So there is a lot of connections with the different people that use visualization tools. Yeah.
Hello, do we have any more questions now? Let me check the web chat or YouTube. I don't think so either.
No, I just want to, here it's Ulysses Ada. I just want to thank you so much for your great presentation. I had a concurrent meeting, so I was out of the room for some time. That's why I asked Bernardo to help with the sharing. But thank you so much for your time and the really excellent tutorial.
No
You
worries.
didn't finish yet. So that's in the middle of the way. Sorry. Okay, so go on, continue. Because I'm seeing questions.
No worries. I mean, we've been having a lot of discussion. I thought that it was interesting to have this and to show things live, not just the videos. I think I can show other usages if you agree with that. We have a little bit of time, so I can
Yes,
show.
we have time, please.
Yeah. Okay. Wait a second. Where was I? Okay, this one, or. Yeah, this one. Okay. So, so again, from Aladdin Light, now I'm choosing an object that I like, Wolverine 110. I have it here. And so I think I answered already a question by saying, like, here you can just hover on the object and then it will go, it will study it. So it will create a link to the Simbad database, and it will show us now that it is a Wolf-Rayet, the HD number, and then I can click and go to the Simbad database. But also, okay, wait a second. Yes, I'm clicking. I'm going to skip through that because I think we have seen that. Okay, maybe not all of it. So, oops, sorry for that. So, there is something important also in Simbad that I wanted to show. So here, so Simbad, okay? Wolf-Rayet is a type, and here we have the identifiers. So all these things here are different names for the same source. So we keep a dictionary of synonyms. And here, those are the references. So 160 papers, 160 publications have information about this Wolf-Rayet star. So I just clicked, and then I can go directly to ADS and then have access to the publication that cites that star, and then just check the paper. So I think that's important to make that connection with the publications. That's extremely important because the data comes from the publications, from the archives, from the users, from the astronomers. And here we have information on the spectral energy distribution. Okay, so what does that mean? Is the collection of actually, we don't call it a spectral energy distribution at this level because it's not corrected for some differences in the instruments and the PSF and such, but it's a visualization of the photometry of that object. And so actually what's going on behind the wheels is all the catalogs that are available in VCR are being queried around the source, and we keep information on all that data from all those catalogs so that we can combine it in energy and wavelength. So, it went back. So, oops, okay. So, okay. So now what I can do is that I can have access directly to the photometric information by clicking on the data, and here, down here, I have photometry information of all the filters that are behind. And here, that is just the photometric data point that in this particular case comes from this catalog of infrared point sources. So that would be that individual data point, all the information that we have around it. I can go to the README file. It comes from that publication. For each individual catalog, we have Jupyter notebooks. So for those that are doing programmatic access, that can be very interesting to see what can be done via the example Jupyter notebooks that we have. And we can have access to all the table, the whole table with all the sources of that catalog here. And although we have seen something similar, I want to show you something that we haven't seen yet. So, okay, that is a table. And now, do you see this little antenna here? It says send to VO tools. So I can click on it. And now it says, do you authorize connection? And if I say no, well, it won't. And if I say yes, then I can broadcast the data. And what does that do? That sends it directly to Aladdin. So now I have that table here in my stack. So I have all of the table, the whole table down here. So I can visualize the different photometric points of different sources in the sky. So that is also a protocol that VO tools typically have, is SAMP, and it sends it from the web to the tool. And if I had more than one VO tool, it would send it to all of them at once. Okay? So I think that is a very powerful thing because, for instance, now I could also send it to tools such as TopCat, which is a better tool for visualization of tabular data. Okay. And that was the part that I wanted to show about SAMP. So, but I think what I'm going to do is to show you how SAMP works in live. Okay, so I'm going to open two tools, Aladdin and TopCat. And here I'm going to open for instance, I'm going to limit to 50 sources, Gaia, submit, and I'm going to send it to tools. Okay, so I'm going to say yes. and then I'm going to broadcast. Okay. So here, now I have in TopCat my table limited to 50 rows because the service, I said that it should be limited to 50 rows. And the same here, my Gaia table limited also to those same 50 rows. And now I'm going to put here Gaia. I don't know if I have that. Okay. So I'm going to load here the Gaia flux map and my data points here. And here in TopCat, I can visualize the tabular data, okay, the content, and I can plot things. So I can plot, for instance, okay, by default, it says, okay, write extension and declination. But maybe it's more interesting to say, I don't know, the parallax of these sources. Whoops, maybe not. Against what? Or proper motion and proper motion. Okay. Why is it not so? Okay, I'm just making a little trick so that. Okay, I don't want this. I just want all that. That's a bad choice of plotting. Wait a second. I restart because I don't like to have only one source in my subsample. Okay, all of them. And I restart. Okay, it doesn't matter if it takes that against that. They're very nearby, all the sources. Why are they also all nearby? So I don't know if you can see this, but as I move here from the source, it also is moving in my panel here. So if I move here, it will highlight on the other tool the source that I'm looking in the tabular data. So these tools are connected. And that means that if I was visualizing different regions in the sky, I would see huge differences in both here, and whatever it is that I would be plotting here. Unfortunately, the example was not the best, but I just wonder if I can flux. Okay, here. Now, this is a better choice. So here you have the different sources in this diagram. And so I can click on them and automatically it selects them in the table here and also in Aladdin. It doesn't seem to be doing much, but it is. I do not. Yes, it is. Sorry. There are a couple of tricks that one needs to do. Okay. For things to work. There you go. Finally. Okay. So now you see the two panels are interconnected. So for instance, if in my table, imagine that this was, I don't know, a list of targets to be observed at the telescope, and I sort them by brightness, and then I just can visualize them one by one in the sky. Okay, and I think with this, I don't know if you have any questions, but I see that we're at 8:30. I still have 10 minutes, right?
Yes, you have 10
Okay,
minutes.
very good. So then Okay, so this was a little bit of the interoperability between the different tools and services. And now, if, oops, yes. So if you would like to make your own images, progressive catalog, you can do it yourself. There is a very relatively long tutorial, but easy to follow, that helps with simple images from a survey, how to create that heaps, and even how to publish it so that it would be available through tools. So here you have, so the idea of this tutorial is to create heaps mostly, and to visualize them, and then compare and combine the data. So for this tutorial, you would have to download the data sample. The data sample has only 6 images to facilitate and to make it faster, but you could imagine doing this with all the Pan-STAR survey. That would take a month to create the heaps, but it's doable. But yeah, so you can download these images, download the needed tools. Okay, so here are the requirements. So HeapsGen and Aladdin Desktop, and you can create your own heaps. So for that, what do? So you download the images, you put them in a particular place in your computer, you need to have a little bit of space, and then you launch Aladdin, okay? So now, I have the images here, the 6 images, okay? So I'm going to do this. I'm going to launch it with sufficient memory, of course, because it's not there. So I'm going to launch them with sufficient memory so that it won't give me trouble. And now I'm going to create, there you go. I'm going to create tool, generate a heaps based on an image collection. And here in the source directory, I'm just going to paste, oops, not this, but the location. No. Okay, the location of my files, okay? Okay, it recognized it automatically because in the target directory, it created the same thing, so data isophoto, but now it added heaps, okay? So it's going to create a directory and the data name is going to be isophoto. And here, what I'm going to do is that I know that the images have some values that are null values, and I'm going to put them to 0. Okay, and now I'm going to choose the resolution, the maximum resolution at which I want to create the heaps. So by default, it reads the headers of the images. So it's proposing a value. And then, okay, so I'm going to say start. So it started the sky tessellation. So the cutting of the images in different cells at different resolutions. Okay. Okay. So the more files you give it, the more time it will take, and the more space it will need in your computer. You see here the space required in this particular case with the images is just 650 megabytes. But if you go to a higher resolution, then you have to multiply by 4 because this cell is divided by 4. Okay, so there. So what does it say? Okay, it did it. So, oops. So what it creates is those files, okay, with different orders and so on, but okay, that's just where the files are, so we can investigate just manually, but it's not very it's not speaking so much, but it's the fits images and then the PNG images. And so now here, what I can do is I can load a local file. And now I'm just going to select the hips. And I'm going to choose it. And there is the hips, okay? So that's the hips that I just created based on some images, on 6 images. So now I can, for instance, also show you load a local file, what one single image is. Okay, so that would be the single image and the hips. Okay, so that's the single image. Okay, so we have 6 images covering different areas of the sky. And now here we have access to the other ones. And you see here how you see the pixel cell. So, oops, sometimes there is a little bit of latency the first time that is visualized. There you go. And so now here my fit image had values to you see it in the corner up here, okay? There are values and it's set to 0. So what I did is I masked the values so that I put them like in an alpha vector or something and they're not shown. So the hips overlaid on top of the images. So if you have images, if you're creating images and you have coordinates on them, you can create this type of progressive access to the images. And in this tutorial, so I will not do the rest of the tutorial, but you can do other things. So you can do the same type of exercise for a catalog. That is very interesting. And you can even go all the way to publishing the data with Aladdin Light, okay? And here you have a snippet or how it can look like. So, and you can just like, oops, copy paste this into, whoops, what am I doing here? Copy paste this. And then just open it. And that would be, so I have it, I did this before, right? So I have the catalog and then I can visualize things using Aladdin Light. Okay, so do you have any further questions?
A quick question here.
Mhm.
Thank you for the presentation. It was very good. I saw that some things, some softwares you run on the browser, and I think one software you run on Java locally. I would like to know if all these softwares are compatible with Linux, since you are using Mac.
Yes, so that they are compatible. Yeah. So I work with Mac. So I know that this would work with Linux, with Mac, and with Windows. Yeah. And every time that there are new versions of either Java or, well, not Java anymore, but of Mac, we test them as soon as they become available to see that things keep on working. So and of course, if you would see anything that is not working, we have a support address. So you can always drop us a line, or we also have a GitHub. So we welcome all the feedback that you can give us is good. So if something is not working the way that you expected, or if something is seems to be crashing, just drop us an email and we will make sure that we can help you.
Okay, are you finished now?
I think so. Yes.
Let's thank Ada for the presentation.
Okay, wait.
Are there any more questions from the audience?
No, now I just want to make my comment in the appropriate time, Ada. Thank you so much for accepting the invitation and for giving really a nice presentation. It will be very useful. It will be on our YouTube, so people will be going back to that often, I think, to follow the tutorials. Thank you very much. And this will be very helpful for the rest of the event as well, as we are going to deal with HIPs in the hackathon. So thank you very much.
Okay. Thanks a lot for the invitation, and thanks a lot everyone for all your questions and the interaction.
Thanks a lot, Ada. So we have a coffee break now. We'll be back at 4.
Okay, so we are back to a little bit of a different session, and we wanted to give the opportunity for, let's say, external people to present their work, what they're doing, so that we know a little bit more about the work that you're doing or other initiatives. And today, the first presentation, the first contributed talk, I'm very happy to have here Aline Veloso from the Brazilian Space Agency, who also has a lot of activities for capacity building and outreach. And she's going to tell us about one of those. And thank you very much, Aline, for being here. And you've been following the event for most of the time, I think. I've seen you connected remotely all the time. So thanks a lot. I hope you're enjoying it and that we can partner more in the future. But tell us about what you're doing at the Space Agency in capacity building and education outreach. Please.
Thank you. Thank you, guys. Can you hear me well?
Yes, we can hear you. Your video is a bit broken, so maybe at some point we can switch the video if the bandwidth is too heavy on the bandwidth.
Okay. Okay. So may I share my presentation? Okay, you guys, can you see my screen? No?
Sim.
Yeah, okay. Thank you so much for introduction. I'm Aline Veloso. I work for Brazilian Space Agency, and I coordinate of the competencies, capacity building, and technology development in the Space Agency. And I've been there since 2018, 16. Yeah, it's kind of a bit while. And I go talk about the programs we have for space education and outreach called AB Escola is the name of the program. And the program is in the space since 2004, so over 20 years. And you bring for students, undergrad students, and community in general to talk about the space and the space exploration. And our programs is continue from this 20 years in different views, different projects, and I'm gonna talk to you guys a little bit of them. And one special one we have is called, em português you say, Centro Vocacional Tecnológico Espacial or Space Technological Vocational Center. Is a kind of space camp, but it's a one-day space camp is located in Natal, in northwest of Brazil. So here in Natal. And we receive students from different ages, from elementary school and middle school. And we have different programs for the students. One program is called Space Day. So usually students from the north grades, almost the students finish the middle school, and the next years they go to the high school. So it's teenagers 14, 15 years old. And they spend the whole day in the camp learning about space exploration, the Brazilian space program, and they have contact with the technologies like the CubeSat. They see how to build a CubeSat, how to program it. They have experience with the rovers. We space area called Mars area. So they simulate like a rover in Mars. They can program it, the rovers around there, and they have expressed with the um, rocket with the bottom water, so they can launch and learn about physics and chemistry involved in this experience. Also, we have like a planetary. They can go there and learn about our solar system. So the activity in this space camp begins in 2018, something like that, and we receive about 1,050 students for this space day. Another activity we have over there is astronomy day. This is for young kids, like end of the elementary school, beginnings of the middle school. They go also for a day. They spend of us, they observe the sun with a telescope. They have letters about space, astronomy, and they have some hands-on activity as well. They are young, so you do many hands-on activity over there. So in 2004, we received for this age about 1,000 students. And this year, we start another activity in the center called Teacher Training Day. So this teacher was selected in the region of the Rio Grande do Norte, is the state of Natal. And those teachers are public schools. They are from our public schools, and they will learn how to program it a CubeSat in this center. So be a program for the whole year. And after that, they go to the school and transmit this knowledge and they know the learning in the center for the school or the teachers and the students. Um, Another program we are is the global programs, is an international program, it starts with NASA. The activity from Global started 2000 or 1995 is a program for study environment. So students are invited to collect data like temperature, humidity, clouds, trees. So a different protocol to fill. So those students are invited to collect this environment data, compare with the satellite data, and build this research to do at school. So actually the activities is 127 countries, over 40,000 schools in the world. So each country here, the qualified ones is a country in the global program, so a huge program. And Brazil started the program in 2015. Now we have over 300 schools registered in the program. Students are collecting data with teachers. So we have over 1,000 teachers registered for the program, over 8,000 students, and a lot of citizen scientists around Brazil. They all collect data, different protocol from the environments. And now we have over 90,000 data entered from Brazil. So we are growing this program. We start like 20 years later, since the program is in the world, but we are growing really fast. And every dot here is a student that collect data from the program. And then we start to work together with the university in Maranhão is another state in the northwest of Brazil, and we start working on a project called Globe in STEAM in Maranhão. Is focusing the Globe programs We start with the Federal University Maranhão in 2023. And today we have over 1,500 students in the program. We involve undergraduate students and professors and teachers in 10 schools in 3 different cities of Maranhão to collect data in the globe and learn a little bit more space. So this is one of those activity we do with them is the bottom water rocket they launch. So you're gonna see the students get really excited. Every time it's just like that. So they get really excited about that. So we start with those demonstration, but they are really doing research in environment. And always, since we are a space agency, we ask them to compare how the space data can help them to understand a little bit about the environment. And another program you do in northwest of Brazil is called Girls in Space. The program starting in Rio Grande do Norte states, but it's growing. Now we are in Rio Grande do Norte, Maranhão, Pará, Amazonas, and Goiás. It's a program for motivated girls and young women to go for science fields, special for space areas. So we encourage them to involve in this program. We have these activities, classes in those fields, astronomy, astronautics, physics, chemistry, and they run the project in school. We have some teachers and professors, undergraduates and graduate students, and even high school students to go to the school. They help others to provide knowledge about space, and they develop their research or technology project in the school. It was an activity we did in February. So we have over 200 girls in the programs. They are coming from those lectures, and after that they go to the school, develop the activity, and we go out through the year to see how they going through the research. In São Paulo, we have another program with ITA, is an institution for technology and aeronautic, and institution for education. We start work with them in 2003, so they support us in these activities. So they do STEAM, we put A because it includes the art for the project as well. So science, technology, engineering, art, math. They do a workshop in different areas, and thus students go back to the school. They teach all the students. So we have like young students teach other older students and to talk about different areas of technology and science. So there's another program. And with the universities, Brazil has now 7 undergrad programs in the aerospace engineering, and 3 postgraduate programs, graduate programs. And we support the universities with program to build and reprogram CubeSats, and also experimental rockets. Yes, someone want to ask something? Can you guys hear me well? Yeah. So are you continuous?
Yes, yes.
Yes, okay. So those those are some CubeSats we launched already. Cephis was launched a couple of years ago, and now we finished Aldebaran with the Federal University of Maranhão. PTQSat is with Minas Gerais University, and we also support a Olympic called Ovesat. Is a knowledge of Olympians about satellites with young students as well, and universities students as well. And then we, in 2021, we launched our educational platform. This was launched because we was in the pandemic moment, so it was really difficult to go in school, do activity with schools. The schools in Brazil was all locked down, so we start to work with the online capacity building. So and then we offer in the platform classes, is classes online, and so everyone can go there and take classes. Today we have over 18 classes open, so we now with open classes until April 30. And we have over 20,000 users in the program, in the platform. So registered users. So it's kind of growing. We start really small, but now we have a lot of using the platform. And the classes is focused in aerospace science. Everything is about space, but we divide in categories so they can learn a little bit more, even like humanities and social sciences as well. So those as the classes we are open now. The classes are all in Portuguese, but they can get translation easily with any online tool. Even the video, they can use a subtitle to learn about subtitle in the videos to understand it in another language. As well, we have using the around the world. So from these 20,000 registered users, and 95% is from Brazil, and the audience, but we have using around the world. And we take some statistics to understand who is the user in the Brazilian IB Scholar platform. So you see the major is still a male, 34% is female. And to understand a little bit more about who is coming to our class. Our class was in the beginning think about undergrad and graduate students, but after a while you see different ages, even young kids or older come to learn those classes. So each class is in different fields, but also we provided what is the public for these classes. So we have classes for young kids, for teachers, for undergrad, graduate students, even professional in the space area, assessing to learn a little bit more about the area the classes are. So majors are students for the professional, and majority is undergraduate students. So we have a few, still some professionals or even undergraduate teachers, but the majority is students and undergraduate students. And this is my contact. If you guys have any question or would like to know a little more about our activity, I invite you guys to go in our platform, see the classes, see if you are interested to give a classes for us. We can open this opportunity and spread the word about space, astronomy, and astrophysics.
Thanks a lot, Aline. That was very nice to see all the things that you're doing. Are there any questions? So if there are no questions, I have one. So how do you see that we can collaborate in the context of the open universe? I mean, you do lots of things. You have a very big reach of public and you have experience in many fronts. So I'm sure there is something we can do together.
Yes, sure. Also, I think we doing some classes in our platform open for everyone interested in. So, saw some tools those days, really interesting. So we can spread the word about it. To teach a little bit more longer, have classes for specific publics, specific people, and we can support them by our platform. And also invite to talk with our students. For example, the Girls in Space. Just before the break, we have an amazing lecture with the professor, and she talked about if she can go talk about a bit about her experience with the kids. We will be really happy to have her learn about more about her research and everything else. And any point, even if you want to go with the students together, talk a little bit with them, or build their classes for a high school students or for university students, we are open for all kind of collaboration.
Good. So let's keep in touch after this.
Mhm.
And there is another question here.
Hi, Aline. It's Jamie Conway from Mibaki here.
Yes.
Hello. We've just become one of your STEM professional groups. So I would help you engage with Ulysses however we possibly can. If you need a hand, just give me a shout, okay?
For sure. I take your contact with you. We'll be glad to have you and have a meeting and talk a little bit more how we can collaborate together.
I don't have a question, but I have to say, it is muito obrigado pelo trabalho da Escola Brasileira, Escola Virtual. Eu sou um dos que utiliza esse serviço, acho muito, muito útil mesmo. Muito obrigado.
Obrigada.
Excellent. So connections already exist. Good. So now, thanks, Aline. And we have two final talks, a bit more scientific, of two of the people that are following here. So I think our cosmic ray physicist is the first one. So Mateus, please. So these are kind of shorter academic presentations to show the work. So
Hello, everyone. My name is Matheus Zeferino Renault. I'm a master student from Professor Carola Dobrecait at Unicamp. I work with cosmic rays, with ultra high energy cosmic rays detected at the Pierre Roger Observatory. Oh, it works. Oh, nice. So today I'll be presenting two analyses that I've been doing in my master's. The first one is a large scale search for anisotropies in the ultra high energy sky. And the second is a correlation study between cosmic rays and starburst galaxies. So here we can see the cosmic ray spectrum. As I said, I work with cosmic rays of ultra high energy. So it's this part of the spectrum here in the limit of X electron volts or above. As we know, cosmic rays are generated by some astrophysical source in the outer space, and they can propagate through the outer space until they eventually reach the Earth. During this propagation, the cosmic ray can suffer some deflections especially by electromagnetic fields, and they can also suffer some attenuation. And when the cosmic ray reaches the Earth's surface, the Earth's atmosphere, it will interact with particles in the atmosphere, generating a cascade of secondary particles. So if the primary particle has enough energy, the secondary particles can reach the ground, and by detecting the secondary particles on the ground, we can obtain information about the primary particle and then obtain information about the source that generated such high energy particle. This is what's done at the Pierre Roger Observatory. The Pierre Roger Observatory is located at Argentina. We can see here a Warren-Cherenkov tank at the observatory. This tank is a part of the surface detector station. At the observatory, we have around 1,600 Warren-Cherenkov stations, surface detector stations, spreads over an area of about 1,000 kilometers square. We also have some 27 telescopes, 27 fluorescence telescopes. By using this hybrid technique, we can measure the energy of the primary particle with precision above 14%. So in this first part of the presentation, I'll be talking a little bit about the search for large-scale patterns in the cosmic ray spectrum. So here we can see a little bit of our data set. For this first part, I used a data set of cosmic rays detected from 2004 to 2022. So 19 years of data taken and energies. And for this presentation today, I will be showing data of energies above 8 ex-electron volts. This is the same data set as the one used by the collaboration in the last publication, in the last paper that was published like last year. So we can do a pretty good cross-check. And when I'm gonna start like looking at, when I'm gonna start to search for patterns in the cosmic ray sky, the first thing that we have to do is to look at the sky and see if visually we can like find some pattern. So I calculated the cosmic ray flux above this energy, and I plotted it here for you. We can see here that apparently there are more cosmic rays coming from this direction of the sky, so a declination of about 19 degrees. And apparently there are less cosmic rays coming from the opposite direction. This is what's called a dipolar pattern. So the idea of my research is try to model mathematically this pattern, to model mathematically the flux of cosmic rays, and to try to like use some statistical test to see if this model that I'm gonna make, this favors the isotropic model of cosmic rays coming from all directions of the sky. So to model the cosmic ray flux, I expand the flux into a spherical harmonic series. First, I truncate this series into the dipolar order, and then I truncate it into the quadrupolar order. To do this expansion, I expand the cosmic ray flux in both right ascension and local azimuth angle into a Fourier series. So to do this expansion, I have to go through a non-trivial procedure since here we are working with experimental physics. So I need to consider both the inclination of the terrain area below which the detectors are assembled. So since we are we have more than 3,000 square kilometers of area, and I also had to consider the variation in the number of active detectors around the 19 years, because I said we have like more than 1,000 detectors at the observatory. So here I show a little bit of my results. We can see our data for right ascension here. If the cosmic rays were coming from an isotropic distribution, we would expect like some variation of the red points around this mean valuing. However, this is not what we see here. We see that our dipolar model fits well our data set. And indeed, when I run some statistical tests, I find that our dipolar models disfavor the isotropic model by 6.7 sigma. So this is greater than 5 sigma. Therefore, we have here a scientific discovery of a dipolar anisotropy of cosmic rays. This discovery was first made by the collaboration in 2017, and here we have the updated valuing. And a curious fact about this dipolar pattern is that the dipole points to a direction that makes an angle of about 115 degrees with the galactic center. Therefore, this is an indication of an extragalactic source of such high energy cosmic rays. So in the second part of my analysis, I run a cross correlation between cosmic rays and some extragalactic source to test if you have like a higher correlation. And I chose for this part starburst galaxies. As we all know, starburst galaxies have a really high rate of star formation. Therefore, starburst galaxies are a good candidate for cosmic rays like ultra high energy particles. So I used 23 starburst galaxies from Fermilab catalog, and I used cosmic rays detected from 2004 to 2017. So this is the same data set as the one used in the publication by the Auger collaboration in 2018. So we can again do a pretty good cross-check of my code with the one used by the collaboration. And the energy threshold for this analysis is greater than, the energy for this analysis is greater than some energy threshold that varies from 20 to 80 ex-electron volts. So the idea of this analysis is to create a sky map that I'm gonna call an isotropic map, which is our new hypothesis. So our new hypothesis here is cosmic rays coming from all directions of the sky, like isotropically. And as alternative hypothesis, I make a catalog map, which is cosmic rays coming specifically from the starburst. And I send this with an isotropic background to consider that cosmic rays can also come from other sources and not just starburst. This fraction of isotropic background is a free parameter in my analysis. So here I create this plot. We can see here the starburst directions. I put the size of each circle to represent the electromagnetic flux of each starburst. And I also put the color of each circle to represent the luminosity distance of each starburst. So here in this plot, we have like all the information that I used about the catalog. So to model cosmic rays coming specifically from this direction, for example, I assume that this cosmic ray will suffer some deviations, especially by electromagnetic field. So it will like follow some distribution around this mean value. So the distribution that we use it is a Fisher distribution, which is equivalent to a three-dimensional Gaussian distribution. And this Fisher distribution has a parameter that is a Fisher angle that I also use it. So here we can see the map of cosmic rays coming from each starburst. We can see like this, both starbursts sum the flux together. So we can see here the final flux. Also, to create this map, I also consider that the cosmic rays will suffer some attenuation due to pair production and also to pion production with photons from the cosmic microwave background. So I consider this attenuation, the cosmic ray flux, to make this map. And in this analysis, as I said, we have two free parameters. First, the Fisher smearing angle to smear this cosmic ray flux. And second, the fraction of isotropic background that I use it. So I calculated the test statistics for this analysis for all varying both the Fisher angle and the fraction of isotropic background. We can see here our grid search. And I find that our best value is for a smearing angle of 30 degrees and a isotropic background of about 19%. So I ran all this analysis for all the energy thresholds from 20 to 80 with a step of one x electron volts. And I calculate the test statistics for this analysis. So our best value is found for energies, cosmic rays with energies above 39 x electron volts. After that, I consider some penalization in our analysis due to the search in all the energy thresholds. So after considering this penalization, we find that our model disfavor the isotropic model by 4.1 standard deviation. This is not 5 sigma. We do not have here scientific discovery of correlation between cosmic rays and starburst galaxies. However, we have here a clear evidence of such correlation. So to sum up, I did two independent analyses. In the first one, I looked at the sky and I calculated that we can describe our data set by a dipolar pattern. And this dipole points to the direction that makes an angle of about 150 degrees, 15 degrees with the galactic center, indicating some extragalactic origin of cosmic rays with ultra high energies. And our dipolar model, it favors the isotropic model by 6.7 sigma. And after that, in the second analysis, I calculated the correlation between cosmic rays and starburst galaxies. And I found that our model, considering these parameters for the map, disfavors our isotropic model by 4.1 standard deviation. That's it. Thank you. I will be very happy to answer any doubt here or in the coffee. Thank you.
Yes, you can also ask questions before because you have to wait for the coffee of tomorrow.
Okay, so can I ask all the questions you want today or tomorrow?
No, that's a joke. So thanks, Mateus. I'll have to tell Carola that you made an excellent presentation. So
thank you so much.
And well, I have a question which is obvious. I mean, for many times we thought of and even talked a bit with Fourier people to try to bring some of their data to open databases like an open universe. So from your experience, do you think that with Fourier data, do you think it's easy to integrate and there would be some openness from the side of the collaboration to use the cosmic ray events in an open platform like this to integrate with other kind of astronomical data?
That's a pretty good question. I cannot talk in the name of the collaboration, but in the collaboration we have some politics about open data. So there are some data, especially some weather data that are already 100% open. The cosmic rays directions and energies are not like 100% open. We have like 10% of the data released. But there are some papers, like I believe last year, there was a paper about cosmic rays with energies above 32 ex-electron volts. And all the data used for such paper is available for everyone that wants. And there in OG website, there's a really good page about open data. So they put some Jupyter notebooks. They teach a little bit of how the analyses are done, and they like they give to everyone like 10% of the data set. I don't know when this number will increase. I know that it will go to 100% someday. Like I don't know how many years, but it will like increase step by step until it reaches 100%. Okay, good. So maybe we can talk also with Carola. Maybe we can tell her a bit about Open Universe and see what she thinks we can do together.
Mateus, what was really nice in your presentation there? Can we go back to the starburst image?
Of course. Say what?
Yeah. What's go forward to? Forward. Yeah. One more. What's really nice about that, and what I would find really interesting to understand is, did you look for any Lorentz configurations? Because there's an automatic triangulation that you have there that we find in water, and we always try and look at what might generate that relationship across space without looking at time. Did you look for anything there?
Sorry, I didn't understand.
Let me show you. I can point at your drawings.
Yeah, of course.
A Lorentz configuration in space-time generally finds that you have areas of stability in an unwise, an unstable area of space, generated about a central area, which I guess, I don't know, I guess has something to do with the way that time is manipulated by space in such a way that it arranges itself. So now that we're talking about cosmic rays and things, I think it's really interesting how, as a visually acceptable person, I find a direct relationship with what you're looking at in a kind of spherical field in terms of what we call a direct ray. But you've also already got what appears to be a Lorentz configuration. Did you look at that?
No, I didn't look at that. Like general relativity is not a thing that I work so much. Here we can see this pattern, especially because of the high electromagnetic flux. As I said in this last slide, the size of the circle represents the electromagnetic flux. So here we have two galaxies with a higher electromagnetic flux than these others. So this creates this pattern, and also the luminosity distance, because like these galaxies here are like very close to us in comparison with these others. So they will be like less attenuated. So this pattern comes from this. About general relativity, I really don't know.
do we know how far? We obviously know you know the direction as being, if it's 115, did you say? So
no, 150 is for the dipole direction and the galactic center.
Okay, so from what would there be a relationship possibly between these three primary areas, and over what sort of distance do you think?
Yeah, I really don't know. I would have to investigate if there's some relation. Yeah.
That'll do.
Okay, thank you. Any more questions? Yes, please.
So, can you go back to it? I want to, first of all, I want to ask about the coordinates of these plots are the same with the dipole plot or no?
No, they are completely different. To start this plot.
No, the coordinates. the coordinates.
No. Yes, to start this plot is in this plot in galactic coordinates.
The other one I
The
don't.
other is equatorial coordinates.
Okay, so if you change the coordinates,
Yeah.
put all of them in the same coordinate,
Of course.
this dipole is the same that you are getting from the other one? Like
Unfortunately,
you are getting a hot spot in your next plot.
yeah, unfortunately, it's not. I already checked.
Basically, I don't understand. You are getting a hot spot from the local universe.
Yeah.
From two galaxies.
Yes.
And you are getting a dipole from the general analysis of the data.
Yes.
If this dipole exists because of this hotspot, because of the local
Yeah, we would
ultra high energy cosmic ray accelerators in the universe, so basically they should
point to the same direction.
Compatible with each other.
Yes, they
Right.
should. Yes, they should. Unfortunately, they are not. I don't know exactly the number. I should have put it here, but this plot it looks better in the equatorial coordinate. Because of that, I let it in equatorial coordinate.
Yeah,
but
of course. I'm just asking if the hotspot is compatible with this plot or not.
No, it's not. This plot is in for cosmic rays with energies above 80 exelectron volts. The other one is for 3090 exelectron volts. So they are kind of different data sets. Like the other is inside this because it's greater than 8, but other data set. And also this first analysis is considering large scales. So the dipole is a large scales analysis. And in the other, we have a small scale. Because of that we have like a scale of 30 degrees, more or less. So, and the dipole is like 180 degrees of scale. But thank you for the question. Does someone else have any question? If not, we change. The person who is asked the question is now going to give the talk. Excellent, thank you. Thank you, Mateus. And now we have Amir from PUC here in Rio. And he's going to tell us also a little bit about his work and research. It's not your work and research. I thought it was. Okay. So.
Now it's working. In fact, I don't know if would be project that I would contribute or not. I work. So, as I said, I'm going to, first of all, this presentation is within the field of multi-messenger astroparticle physics and high energy phenomenology. So it would be a bit different from the mainstream of the workshop. But I want to emphasize through this presentation, I want to emphasize on the importance of the gamma ray and X-ray astronomy. The title of the presentation is Where do ice cube neutrinos come from? And the possible correlation with the MEV gamma ray and X-ray emission. Let me begin with the title. Where do ice cube neutrinos come from? If I ask you this question, probably all of you would tell me that the neutrinos, the ice cube neutrinos are coming from the astrophysical sources. Correct. But the problem is that except two cases, none of the ice cube neutrinos could have been traced back to any known astrophysical sources. So basically, again, where do ice cube neutrinos come from? This presentation, before I start to talk about what is happening, this presentation is based on these two papers. As I said, none of these two papers are my works, but they are my colleagues. Arman Ismaili is my supervisor. Antonio was my colleague in PhD. Pasquale Serpico is my colleague. Kohta Murasa also. First of all, I will give you a big picture of the multi-messenger. What is multi-messenger in astroparticle physics? And then I will go through the ice cube. Neutrinos ice cube is observing. I go through the Fermilat, the gamma ray that Fermilat is observing. And then the connection between the neutrinos and gamma rays through a multi-messenger approach. What is the connection? And then I will show you, I will try to convince you that there is a tension between the ice cube neutrino flux and the gamma ray from the Fermilat. At the end, I will remain with the question, with the big question. Are the neutrino sources opaque to gamma rays or not? At the end, there is an idea. I will talk about this idea. The idea is not originally from me also. So basically, nothing is from me, but it's interesting. Okay. Let me begin with this. Till 70 years ago, the only messenger the only cosmic messenger we had from the sky was photon. But after that, we developed the particle physics, and we know that right now, the astrophysical sources are producing a tapestry of the particles within the standard model. Let's talk within the standard model of the particle physics paradigm. Let's just distinguish our paradigm. So basically, we know that the astrophysical sources can produce all of the particles. Some of these particles can reach us on Earth, including photons, neutrinos, and cosmic rays. By the cosmic ray here, I mean charged particles. These charged particles can be nuclei, proton, helium, oxygen, nitrogen, iron, heavier than iron. I don't know. We don't know. Nobody knows, actually. Photon and neutrinos. And the multi-messenger approach in astroparticle physics is basically talking about the relation between these particles. And this relation is coming from the particle physics. Basically, the microphysics of the particles interaction is determining the connection between these particles. So basically, here, it is one of the most important examples of the relation between the particles. A proton can interact with the photon, and then you will have some pions, neutral pions or charged pions, and then pions are decaying to photons or neutrinos. So basically, you can see here already, there is a connection between the neutrino flux and the gamma flux, right? From the same interaction, the neutrino and photon. So there should be a connection. Also, from this plot, you can see the cosmic ray. Matheus showed the whole plot of the cosmic ray. I'm just showing the ultra energy part, the neutrino flux, and the gamma ray flux. The fluxes are comparable with each other. So basically, the shape is almost the same. The flux, the amount of the flux is the same. So basically, you can say that maybe there is a connection with it. Let's go further. Ice cube. Ice cube is a neutrino observatory down in the ice of Antarctic, in the South Pole, between the 1.5 kilometer to 2.5 kilometer. And it consists of 86 strings of digital optical modules, DOMs. And these DOMs are detecting Cherenkov radiation, basically. Charged particles are moving faster than the velocity of the light inside the ice. So basically, the DOMs are detecting this Cherenkov light. And here are the morphologies of the events that IceCube can see. So basically, IceCube is detecting neutrinos via these morphologies. IceCube can detect the astrophysical neutrinos as detected, firmly established, and the flux for the moment, is compatible with the power law flux, as you can see here. This power law flux. I'm not going through the details of this. The whole stuff is too much, but the assumption behind this flux is that the flux is isotropic at Earth, and neutrinos and antineutrinos have identical fluxes. On the other hand, Fermilab is observing the gamma rays. Fermilab is a gamma ray observatory. The gamma rays are reaching to the Fermilab. A part of these gamma rays are reaching from the galactic center. A part of this gamma rays are reaching to the Fermilab from other parts of the world. So basically, I can do something. I can have a model from the galactic part of the gamma ray, reduce this part from the Fermilab, and then at the end, I will remain with the extragalactic part of the gamma rays. I call this part EGV, extragalactic gamma ray background. This extragalactic gamma ray background, we know basically that there are some conventional sources, astrophysical sources, known astrophysical sources from the catalogs that we have that are contributing to this EGB, this extragalactic background source. So basically, we know that the blazars, thanks to Mikel yesterday, talked about the blazars, active galactic nuclei, and so forth. We know that blazars, radio galaxies, and star-forming galaxies are the most important, the most prominent contributors to the EGB. So basically, I can remove this known flux from the EGB, and still I will remain with the part which is isotropically diffused in the whole space, in the whole map. So basically, I'll call this part isotropic diffuse gamma ray pattern. By the isotropic, I mean, whatever the direction you look at the sky, you get the same flux. I call this IGR, okay? So what I want to say is that based on the first slide that I said, there is a connection between the neutrinos and the gamma rays. Whatever the astrophysical neutrino sources are, when the neutrinos are produced, neutrinos are believed to be produced in the hadronic processes, like the one I mentioned in the first slide. For example, the proton-proton interaction or proton-photon interaction. So basically, we know that there is a connection. If the neutrino is produced, there should be a counterpart of the gamma ray in the gamma ray. And you can calculate that this is the relation between the spectrum of the neutrino and gamma ray. But the gamma ray at the high energy, larger than the TeV energy, cannot propagate in the universe for the cosmological distances larger than the scale of the galaxy. Because it can go through interactions with the CMB, the cosmic microwave background, and the total background light that we have in the universe, in the local universe, we call it EBL. So basically, there is a background, low energy photon background. These high energy photons that are produced in the source can interact with this background, producing a pair of electron-positron, and then this pair of electron-positron again can interact with the same low energy photons, shooting these photons to the high energy. So there is a cascade of particles here. This phenomenon is very famous. It's called the electromagnetic cascade. So basically, if I have the neutrinos, I will have a counterpart in the gamma ray, which energy, because of the electromagnetic cascade, will be degraded below TeV energy. Fermilab is observing the gamma rays from 100 MeV to 820 GeV. So basically, Fermilab should observe these gamma rays from the cascade. It should be a part of that IGRB that I talked about, this diffuse. You do the analysis in these two papers that I mentioned. They did the analysis, in fact, and you can see that with these plots. Basically, there is a tension. What IceCube is seeing should be in the color region, but what we calculate for the with the Fermi should be below these black lines. So basically you can see there is more than 2 sigma, almost more than 2 sigma tension between the neutrinos from the ice cube and gamma ray from the Fermi. What is the result? The result is that there is more neutrino flux than the corresponding gamma ray flux if they were produced from the same sources. So there is a tension, there is a problem. What should we do? One can deduce from this statement here that the gamma rays probably are not escaping from the source, right? Because we have more neutrinos than the gamma rays. So one possible scenario, one possible answer to this question would be that the gamma rays are not escaping from the source. So how can we justify this model? If I have a dense photon field inside the astrophysical sources, then the gamma rays that are produced via the hadronic processes that I mentioned, that are producing also neutrinos and the gamma ray part, before being emitted by the astrophysical source, going through the space, interacting with the CMB and cascading, before all of these stories, inside the source, there is a dense photon field that the same process, the same electromagnetic process can happen inside the source instead of outside of the source. So basically, and this gamma ray, because of this electromagnetic cascade inside the source, can degrade its energy to below GeV escape, MEV, KeV, X-ray, something like this. So what can we do? We can go through our catalogs of the X-ray and MEV and check if the neutrino sources are correlated with these catalogs or not. This is one of the ideas that people currently are working in there. So basically, we need these catalogs. We need this X-ray astronomy and gamma rays to know, to be able to say something about the sources of the neutrinos. And here I want to mention some of the works that have been done during these years. Basically, I just read from here. In this paper, in the first paper, they did a re-examination of the discussed analysis, and they got the same result, as I said. They got the tension between ice cube neutrino flux and Fermi-like gamma ray. In the second paper, basically, it's an analysis of sub-millimeter, mid-infrared, and ultraviolet observation of central 50 parsec of NGC 1068. NGC 1068 is one of the exceptions that I said neutrinos are not couldn't be traced back to the astrophysical sources. For the NGC 1068 is one of the sources that we are seeing both neutrinos and gamma rays from the source. So basically, they are doing the analysis, not the gamma rays, sorry, just the neutrinos, but it could be traced back to the source. So basically, they do the analysis with the multi-waveband observation, and the result is the central region can be gamma ray obscure. Also, in the ion acceleration in the hypernebulae, they got the same result in this third paper. In the last paper, if you remember, Matheus was talking about the dipole from the cosmic rays. So basically, they have considered the Fermi-lat catalog, and they try to reproduce this dipole with the whole catalog of the Fermi-lat. But the problem remains. Actually, the result is that we need an ultra-high energy source population opaque to gamma ray. So basically, for the moment, this scenario is the most favored scenario in this problem. And thank you so much. Sorry for being late.
Thank you, Amir. I don't know if there are questions. You got.
Thank you so much for the presentation. It was very good. It's like a personal question. If you know, how did you do the, you said that it was not you that did the analysis, right? And if you know how the one that did it model the interaction with the CMB, because I'm having a lot of difficulty with the partons distribution in the LHC model.
By the interaction by CMB, you mean the electromagnetic cascade?
Yeah.
So the electromagnetic cascade is more ultra energy regime I have put in. So basically, electromagnetic cascade, the conventional one is that you have the photon. You can solve it in two ways, basically. First, semi-analytic. You will write the transport equation, solve the transport equation.
Yeah.
Like the one that has been done in gamma cascade, if you know, G cascade. So you can use G cascade if you want. If not, you need to write a Monte Carlo algorithm. So basically, or pure numeric or semi-analytic. In the Monte Carlo, it's like that you have the probability of interaction. A photon is coming. There are various interactions at the root triangle. For the conventional one, you have just one interaction. And then it's going through the pair production, and then each of the electron positrons that are produced are going through inverse confidence scattering. You have the cross section, you have the inelasticity. By the inelasticity, I mean the fraction of the energy that goes to the leading particle at the end. So basically, we calculate all of these outgoing particles' energy, and then you get the flux of the electron positron. But the most simple way to calculate the cascade is the cause, G cascade, CR profile, my code Mieka for the ultra high energy.
I would ask about if you were using CR propa.
CR propa. CR propa is complicated. CR propa, I have used CR propa. For the electromagnetic cascade, I don't suggest CR propa now. No. For the electromagnetic cascade, I suggest gamma cascade. G cascade.
That's great. G cascade. Thank you. Good. I just have a final comment. You know that Paolo Giomi used a lot his tools, Firmamento, etc., to do search for counterparts of neutrino events.
I didn't know, but now you
Yes.
said,
So if you look up some of his papers, there is a lot of work using Open Universe and Firmamento, and a tool that existed before Firmamento, a bit more rough, but doing the same stuff. To select the error circle, the potential sources, and then doing an analysis based on the SED to associate the probability of a counterpart. There are some nice things there. It could be useful for your work.
This is the most natural way to do this, check this scenario.
Yes. And these tools, they work very nicely because they show you all the counterparts. You can build SEDs immediately and run some code to analyze.
I need to learn that.
Yes. It's very simple. It's very simple. Also, my students here, they have done it for some work, not looking for neutrinos, but for classification of the sources. So it's very easy to use. So have a look at the papers and we can talk if you have any questions. Good. So with this, we close the day. Thank you very much. Thank you to the people connected, and see you tomorrow for the last day of lectures, and then you play with things yourselves. Good, because too many days of lectures is heavy.